every material in town and in the world that does anything topological. And I mean, feel free to share your screen, and the floor is yours. And we're very excited to hear what you have to say.
Yeah, so I'm always the relaxing part of the conference, right? Because this is mainly a theory conference and spread with a few experimentalists showing you what you can do with what you learned, or what you can maybe also tell us what to grow. Okay, so I will give you a little bit an introduction, and I focus on topology. I make small bridges to graphene and maybe twisted graphene. So because there's already a question. Adolfo, you're in charge with the question, right? Okay, so I focus on topology so everybody can lean back, relax, and listen to what we are doing. Now I hope it works. Okay, so you are familiar with the concept of topology, but I still put this slide in because I have seen mainly all the talks were about twisted graphene, but this is also can be seen in the context of topology. And you know, we all look for the topology of objects, and I like to show our picture of the topology of objects. So like this, for example, donut has the same topology as a coffee pot, as you know, because both have a hole, and the pretzel here has 3 holes, and this is the same as this. And this we can apply to not only this object in real space, we can also apply this to the electronic structure in reciprocal space, and so on. And this is all about topology. And this story started now 15 years ago, more than 15 years ago. And I think it really has revolutionized solids. And I think it's not, so far we only see the tip of the iceberg, even when we include the twisted graphene. So I think we maybe can come via twisted graphene also to molecules, organic molecules, and find even more topology in organic reaction or in chemical reaction in general. So it might be interesting in a much broader way. So, and if you want to ask me what is most exciting thing in chemistry, so I'm also a solid state chemist and more on the physics side, but the chemists are mainly excited about chirality of molecules, organic chemistry, because they show very interesting properties and they are very distinguished only on a certain viewpoint. So because you can make these 2 molecules which have exactly, for example, the same atoms, and since the carbon is coordinated tetrahedrally, so the 2 molecules, you can make 2 different molecules if you have 4 different ligands here on this carbon atoms, which are like the hand, the right and the left hand, and they cannot superpose onto it. And so this is the basis for life, because all the molecules in life and even the bigger macromolecules in life are chiral, and the processes like motors in cells are chiral. So chirality is extremely important in chemistry, and this is a viewpoint of topology in chemistry. You have seen the first figure more related to mathematics, and it still is a very open question how we fundamentally have broken symmetry in life, because we all exist only are made by left-handed DNA, and we are all eating only right-handed sugar. So, and it's not so clear how this fundamental broken symmetry has appeared on Earth, and it's one of the biggest questions I still think we have to ask. And maybe there's a connection between the topology we are thinking here in physics also. And one of the, here's the first one of a bigger chiral molecule you learned about is the twisted graphene. Twisted graphene will always describe as twisted graphene, but you can have 2 twisting angles, and this gives you the 2 different enantiomers. So like in the right hand and the left hand molecule, twisted graphene can have the right angle or the left angle, and in the sense it's also twisted. So this is really interesting, and you can even have macroscopic objects like this here, which can be chiral. And so today I will not talk about chiral crystals and chirality in topology. directly, this is more for the introduction now, and the discussion tomorrow and the results tomorrow I will show tomorrow. So, and the only way to distinguish, for example, two different amino acids which have different chirality is by do it optically, because they change the rotation plane of linear polarized light in different direction, and this is why they got the names right and left-handed, and it's whether they change it in the right or left direction. So there are other ways of thinking about topology in chemistry, and this is a slide which Lukas Müschler made, and we discussed this. So there is also in organic molecules, and here we start with the first building block. This is also the central building block of graphene. This is benzene, so which has 6 carbon atoms here, and 1 single bond and 1 double bond. But this picture is the Kekulé formula is not the right picture, because if we would draw it in a different way here with this only these orbitals which building the double bonds here, the so-called p orbitals. So we have here again the carbons and the hydrogen you don't see in this drawing. So then you have the bonding are all the same length, so there's no distinction between double and single bond like you would think here. So, and the electrons are delocalized in benzene. So this we call aromatic, and there are simple electronic counting rules which are depending on the molecular orbital diagram of this molecule. So these are all molecules which have single bond, double bond, single bond, double bond kind of arrangement. So you always have aromaticity if you have 4n plus 2 p electrons, because then you have filled this degenerated state here. And this is interesting because this is a building block of graphene, and graphene we can understood also as a totally delocalized p electron system. So it's like many benzene rings condensators. So we have naphthalene if you have 2 in organic chemistry, and if you have an infinitive number, we have graphene. So graphene is an aromatic molecule. It fulfills the 4n plus 2 pi electron rule. So what chemists like to do, they like, and if we have, for example, rings which have 8 carbon atoms and 4 double bond, they are not aromatic. Even you could think on the first view they are aromatic. They are so-called anti-aromatic. Here the electrons are really localized in the double bonds, and so they are not delocalized over the whole ring. So these are the so-called trickle rules, that you have 4n plus 2 electrons to be an aromatic molecule, and if you have only 4n, then it's anti-aromatic. And this is related to the electron diagram. You can imagine if you fill this half, it's not this best stabilization to have this delocalized. Okay, but what happens, and this brings us to topology, and you will see to the difference between donuts and Möbius stripe, which we will discuss also in solids, is like if we would make a twist in these molecules, and this is possible, organic chemists can make this twisted molecules, these rules for whether something is aromatic or anti-aromatic are inverted. And this is related, so if you draw the orbitals, so you have also to draw the twist. And this is related to some resonant orbitals. If you do a tight binding model calculation, you can explain it. So, and this is possible. So we can make molecules which are more like a donut and which are more like a Möbius stripe. And you see in the optical properties, even the atoms are exactly the same in both molecules, that they are different. So from their optical properties because of their change in anti-aromaticity. Yeah, and in this sense, we, as from the chemical view, we could also understand this, so that twisted graphene now from graphene is aromatic. It has this very nice flat delocalized p electron sheet, and then if you twist it, so you get interactions between the two layers, and you would explain it by all the nice models with flat bands, etc. But you could also interpret it that you now have areas of anti-aromaticity while because you now have not the really delocalized electron contribution. And this might explain that we have this correlated insulators in graphene. And the question is here, can we use the same for describing organic and inorganic compounds? And as you learned today, it's also that you see many more interesting properties like superconductivity, etc., in twisted graphene. But you see already there's a way to chemistry which is not yet gone. So where maybe we can even go from the solid via twisted graphene, but I will focus on the solid since this is my main specialty. Okay, here's another example which I still want to show. Is like that you can also make larger molecules which look like a smaller sheet of graphene than the sheets we use nowadays, and you can give them even by chemical synthesis a twist. And also here you can twist it in two direction, and the luminescence of light, chiral light, is different for the two twisted candidates, which already shows that there's a nice light matter interaction, and there is really the twist with the same electrons also here makes a nice difference. And it's also again a bridge nice from solid state physics via twisted graphene maybe to chemistry, where we have much more to do. Okay, so the important thing is also, and this is your specialty, to see the band structure. So like going from molecules to bonds. So more or less the graphene can also be understood, the band structure of graphene can be understood in a similar way by making nothing else and condensating many benzene rings. And you see the bands are still related to this. We have the sigma-sigma bonding between the two carbons, but we have also the p bonding here. And these are the important bands here around, which leads to the gamma, to the K point, and the Dirac cone in graphene. So what nowadays I think also is a new view on topology, and especially also for us. So before we the people who do also computational material science, they have simply calculated the band structure, and then you calculate some observables like the magnetic moment or the conductivity, how high is the density of states and so on. So, but we use more or less the whole band structure as a black box. But this was already, I have to say, a little bit different if you go to books and papers from Roald Hoffmann, and this is what Leslie, Lucas, and me, I love, and I strongly recommend this also to the physicists. So he wrote very nice papers about organic chemistry and got the Nobel Prize for Organic Chemistry, but he also have helped us to understand inorganics, solids, from a very different view by simply symmetry aspects. And this is more or less the basics for what we can understand and get out of, and it's strongly related also to the concepts of topology nowadays. Okay, so already he looked for features in the band structure which can explain certain properties, and this is more or less what we are nowadays are doing. So like we like to see features. So in the past we also looked for Van Hove singularities. This was my PhD student time when we look for Van Hove singularity to find new superconductors, and nowadays the zoo of features which we are looking. So we shine light in the sense into the black box of the electronic structure and look for flat bands like in graphene, or we to find new interesting material. So it's total new way to see materials, and this opened us to a pathway really to do super exciting physics on many of these materials. And still, I think we are still on the top of the iceberg. So I want to a little bit shine light on different of these properties from the viewpoint of the experimental, viewpoint, and in the topology experimental viewpoint. And I want to explain you a little bit what we are doing in the world of experiment to inspire also the theoretician, maybe a few experimentalists are also here to come up even with more ideas. I already know I get many ideas from Maya and Adolfo, and recently I received a very nice paper from Jen, which I'm discussing now with the optics people. So this is the best way to do science, and it's super efficient and it's a lot of fun. And I think never in the history of condensed matter physics it has worked so nicely that theory can drive the experiment. But since we now understand much more the features in the electronic structure, and still we don't, you see, if you see the spaghetti here, you see, you recognize a few of these features, but there are many maybe unrecognized features or even hidden features in this electronic structure. So, but what I think is also super interesting, we are now looking for surface states and for the phase. So this is very new, and this is my then also recommendation for the future. So we're looking much more now on surface state, but looking also on the phase of the wave function is not fully seeing the aspects, whether we can use a certain phase. And this is especially interesting in the viewpoint, under the viewpoint of chirality, because chirality, the electronic structure, the MO diagram of both molecules, both-handed molecules, is exactly the same. And this is also the problem, because this is the reason the energy of both molecules is exactly the same. So it's not easy to separate them. And there's a big market pharmaceutical industry, since we are all chiral. So also most of the medicamentations are chiral. So it's very difficult to separate them. So, but the interesting thing is the surface state, which you will learn tomorrow, and the phase of the wave function are different. And maybe these are ways to take advantage and distinguish these chiral molecules and chiral crystals. Anyway, so we mentioned already donuts and Möbius stripe and the basic concept of topological insulators, and I'm sure you all are familiar with this, but I like to bring everything together to bring it in a more complete story from my viewpoint. Is like so that so we see this in the electronic structure, as I already mentioned. So in a normal semiconductor, we have a valence band and a conduction band, which was the occupied MOs in benzene and the unoccupied molecular orbitals in benzene. But now, since we have solids, we have bands. I forgot to say this, but I showed this already here. So here we have molecular orbitals, the occupied ones, the unoccupied ones for benzene. Here we have the same situation, more or less, the occupied bands and the unoccupied band for a layer of graphene. They, at the gamma point, they are identically with the MO diagram, but since we have translation symmetry, our bands get an additional phase. So we have, therefore, this very nice band structure. So this is also very nicely described, also how to do this and even draw it by hand, the graphene band structure in these articles of Roy Hoffman. Okay, so we have this conduction and this valence band now, since we have bands and solids, and the band gap, the gap between the occupied and the unoccupied states, depends on the bonding strength. So if we have hydrogen, so this band gap is giant. So we have hydrogen as gas, therefore, and it has a giant band gap, for example, compared to a cadmium selenide, also, which is was the yellow color of the postcards in Germany. So, and you can, but also have the situation that the bonding strengths, even in these binary systems, are smaller. And then what can happen that the conduction band and the valence band overlap. So we have this so-called forbidden crossings here or crossings here. So whether they are forbidden or not depends on the symmetry of the bands. And this is also a common concept which we have, for example, in organic reaction, in organic chemistry, and here we have it simply between the valence and the conduction band. And this is so it also was a concept of Roy Hoffman. He looked for forbidden crossings in the electronic structure in many different crystal structures very systematically, and could explain many properties, but also many crystal structures. Here, since we have materials, topological materials, we have a large spin-orbit coupling because we like to have heavy elements. So then this crossing is forbidden, so we can open up a band gap by spin-orbit coupling. And now we have a band structure which has in the conduction band a part of the valence band and a part of the conduction band in the valence band. And while the normal insulators are symbolized by a donut, this is symbolized by a Möbius stripe. So in the same way, like we have shown it already in organic molecules. So this is happens quite often in heavy elements. So if you go to the periodic table, you see a periodic table behind on my wall. So the heavy elements like indium, thallium, tin, and lead, for example, they are here at the lower part of my periodic table. So the indium is in group 3 and tin is in the same group as silicon in group 4. So this heavy element compound, they have a different valence compared to the same group elements which are lighter, because here we have the so-called outer s electrons, the 5 or 6 s electrons, which are valence electrons. They get, because of relativistic effects, contracted, and therefore the atoms don't like to give them away because they are now very close to the core. It's very difficult to ionize them. So therefore, very often these atoms have valency which is reduced by the number 2, the 2 s electrons compared to the lighter elements. And this is the reason this band here is an S band, which comes more or less in this heavy element compounds much easier down in energy. And we have the situation of a forbidden crossing is much more common in this heavy element compound. And at the same time, spin-orbit coupling becomes larger. So to find more or less what you learn from quantum chemistry, eventually from Maya and Andre, more or less all heavy element compounds are topological. And then if you have this band inversion here, so the conduction band in the valence band and vice versa, so you get new kind of surface states, which are, I have to remove this, which are, unfortunately, here's this little bit, which are spin polarized. And here for the surface states, we have spin momentum locking. So two different spin polarization. These are very special surface states which are topologically protected. So here I stole a slide of Maya, so which shows what does it mean if my spin and momentum is locked, what I showed here in the slide. So spin and momentum is locked related to the surface state. So it's like, so this, so the electrons, which are moving, they cannot be easily scattered into the electrons of the different spin directions. So they are in this sense protected, and this is a topological protection we like to have, and we see also in experiment if we do experiments with these materials. So so now we the good thing is that all the inorganic compounds are in a catalog, so in a database already. Their crystal structures. This is one where we database where we really are ahead. So if we would have this from all the properties of materials, this would be fantastic. But we have a database with a crystal structure, and this could be used. Then was used to do this topological quantum chemistry, and this has helped to identify all the topological materials. And as I already mentioned, all the heavy element containing compounds are topological. If you simply take into account the electrons which are around the Fermi energy, the energy which is exactly the energy which separates occupied and unoccupied bands, and in this sense, if we would allow even doping or alloying of the material, we would end even with many, many more compounds, because then we could more or less turn nearly every compound into a topological material. So this is a totally new design principle, and it tells us already that there are many, many more possibilities to do. Okay, so there's this fantastic band, this fantastic web page. So you can even type topological quantum chemistry.de or FR. You always end up with this periodic table. Here you can click which elements you are interested in. For us, is fantastic. So if you make some new compounds, we simply can more or less, not new compounds, we can more or less check of all the existing compounds, whether they are topological or not. So new compounds are still a little bit of change, but I'm sure soon you can even come up with a electronic structure with the position of the atoms and the crystal structure, and you get the information whether something is topological or not. So bringing again everything back to organics and chemistry to inspire future research in this direction is like also that even Haldane in his Nobel Prize speech, he used polyene, double bond, single bond, double bond, single bond as a first example to explain topology. And especially if you cut one double bond and get radicals at the ends to symbolize the edge states here in this material. And I like this very much because it again shows again the connection between these different fields. So, for his prize-winning paper, as far as I understood, this paper, he used graphene, and graphene again is very interesting, and he could show that what we know in the quantum Hall effect. I shortly will talk about this very briefly also. So you can have even a quantum anomalous Hall effect in some materials where you don't apply an external magnetic field if this material is, for example, intrinsically magnetic. So this has inspired also Kane and Mehle to look into the electronic structure of the same material. And they find even that if you have spin-orbit coupling, you can use this to have this quantum spin Hall effect to have this new topological properties. However, if you think about graphene, so the carbon is very light, so spin-orbit coupling is very small, so graphene was not the right material, and this has inspired then people to look for more materials. So this is a small break where I want to show you, so materials, what are materials, single crystal, organic, inorganic crystals. So what we are doing, and most of the people who are doing the experiment, they nowadays grow very nice single crystals, which you can see here as beautiful examples, or they grow thin films to make these new materials and to have this as a basis for investigation. And this is the way we do this in films. So you need a lot of heavy equipment to grow this in films. But I think now it's also time to think more about topology on interfaces. One easy interface is a twisted graphene, yeah. But maybe one can use also this film equipment to find more moire patterns or more interesting twisted material. So what we do after there is this prediction, and I showed you now all the materials are characterized into topological materials or not, even magnetic. So we do the synthesizing the crystals, what I showed you already. Then what we do is like we look whether this electronic structure is really the one which we observe. This is the best ways to do photo emission or STM's investigation. So you can see here the calculated surface states, for example, from some wide semi-metals. I explain soon what a wide semi-metal is. And this is the APIS, the angular soft photo emission data, which shows a very nice agreement. Okay, on top, we want then to have maybe super interesting properties, the topological material, which shows also superconductivity. And there's a lot of recent work on this MOT2, where we found that this is a topological wide semi-metal and also superconducting up to 10 Kelvin under pressure. And then you want to make, at the end, maybe devices. And this, I showed you, we also want to do the devices. And people are discussing here, especially in context of superconductivity and quantum anomalous Hall effect, for example, interfaces about Majorana fermion. So far, there's a lot of doubt whether we ever have seen this Majoranas, but this tells also the next generation come up with good concepts where we for sure can find them. Okay, so as I said already recently, there was even, despite of the prediction of all the inorganic compounds using a single particle picture, there was this prediction of magnetic compounds. So magnetic is done. most of the magnetic materials is done, the space groups are done. So the interesting thing is now to go beyond the single particle picture. And this is again for the theoretician to go into direction of correlation. Okay, coming back to a little bit more back to the history of the materials history. I already told you, so the graphene is too light to show the quantum spin Hall effect. Therefore, it was interesting to go to heavier element compounds, and this is simply to look for the lower part of the periodic table. So far, the first view was that the elements are not the right way to go because so they are all gases, insulating or metallic, but there are not so many semiconductors which would exactly fulfill the condition. Maybe bismuth comes closest to this, and tin. Here, bismuth and tin in this area are the best materials, but the next idea was to look to binary compounds, and I don't want to spend too much time here, but simply for historical reason for the people who are really new in the field. So, so by starting with bismuth, which is a semi-metal and was not a topological insulator, it was clear that one should look to binary compounds, alloys, to find eventually topological insulators, and this is exactly has happened here with the bismuth selenide, and which has this fantastic surface state as in the scheme, which I told you before, the spin polarized surface state, and this are the experimental realization. So here we have the example material where we have then this nicely spin polarized surface state, which you can draw as a picture here with a nice Möbius type intrinsic band structure of the crystal and this protected surface state, which looked like a Dirac cone. And another picture way of trying to visualize it is here, like to have this spin polarized surface states in this material. And here how the spin and the momentum is locked at the surface state. Anyway, so this we had already. So, but you can now do the same as I mentioned here. So looking for some compound which has this overlap between the conduction and the valence band. And people have worked on solar cells since a long time. So you see you can have many binary semiconductors in the range of visible light, but there are also materials which have a small band gap or a negative band gap. And a negative band gap is exactly what we have here because we have this overlap. And so therefore it was very clear that people looked for this negative band gap compound. So like a normal semiconductor, cadmium telluride, for example, which has a nice band gap, has the S band here, which I told you comes from the pair effect, and the P band here is a gamma 6 and gamma 8 band. And if you go to the heavier element with the band inversion mercury telluride, you have this band inversion. This was the first realization of the quantum spin Hall effect. But as you can see here, the band inversion leads also to a problem. Mercury telluride itself is not a semiconductor, but from semiconductor industry, we know that if we combine, if we build this quantum well structure here, so the thin films of cadmium telluride and mercury telluride, we can build such a quantum well structure. So we get this quantum spin Hall effect, which is exactly here's a two-dimensional version of this three-dimensional topological insulator. We have this spin polarized currents here at the edges. Nowadays, the plateaus are much nicer. Here you see a very lousy plateau. If you have seen the plateaus from the quantum Hall effect, then the quantum spin Hall effect is here not so impressive. But this was at the beginning, and this has led to a lot of attention. And you already learned about Andrei Brunevich, who is also in charge of quantum chemistry and did also give, I'm sure, nice talks about the twisted graphene. Okay, so that this is a super common phenomenon is also shown that more or less the color of gold can be now explained by topology. because you can simply say different from silver. Here you see the schematic electronic structure of silver, non-relativistic versus relativistic. In gold, here you see that in gold, the 6s electrons are much more contracted versus the 5d electrons. Therefore, the transition between 5s electrons, therefore the transition between 5d and 6s is much smaller than in silver. And this is the reason why we like gold much more than silver, because it has a much nicer color. So I like gold very much, so more than silver. And this is exactly, if you see the band structure here of gold, this was a nice project with Bin Hai. So you see that you have here exactly this S band overlap and the P band overlap. And this is the real band structure of gold. So you see that you have also here this band inversion. And if the Fermi energy would be a little bit higher, it would be even a topological insulator. So that the surface states are really connecting the valence and the electron, the valence and the conduction band was shown here by 2 photon electron spectroscopy, because if you see the Fermi energies here, these are unoccupied bands. So we could really show that gold is a topological metal. So, and I always have to make the bridge to my mostly favorite class of materials. As I said, so in cadmium telluride, the S band is above the Fermi energy, and it's nicely seen that in mercury telluride, this S band comes below the Fermi energy, the gamma 6 band. So you have this very nice band inversion here. So you can find now more materials, and this was a baby went historically looking then for related materials to the binary semiconductors. Now you can take 3 elements, 4 elements, whatever. So if you increase the number of elements, you can make simply the same kind of materials. Here's the example going from 2 elements, mercury telluride, for example, mercury sitting telluride, they have also zinc blende structure, the same structure as all the other binary semiconductors used for solar cells or for electronics, like gallium arsenide. So this is a 3,5 semiconductor. So now we could also make them with 3 elements, and this is a so-called Hofhäusler compound. And we can simply have the same electronic structure by simply redistributing the electrons over different atoms. So here's like gallium arsenide. So you can have the same electronic structure like for lithium magnesium arsenide, because it has the same number of electrons, while gallium has 3 electrons, lithium and magnesium has also 3 electrons, so this is the reason. Anyway, if we go to 3 element compounds, this has one advantage, and I think we didn't take advantage of all the properties of Häusler compound, because they have partially also D and F electrons. So we can make semiconductors with 18 valence electrons, which leads to much more freedom of redistributing more electrons over 3 elements, like here in the zirconium nickel tin, a famous thermoelectric material. And many of the thermoelectric materials are topological, more or less, I would say all of them, because p-n-orbit coupling is good for thermoelectrics, and thermoelectrics really are showing nowadays really, again, new promising pathway, because they show very high figure of merit. So these are 18 valence electrons compound, but now you can imagine that I can make the same electronic structure as Molenkamp did with this quantum spin Hall effect in cadmium telluride and mercury telluride, also with 3 elements. We simply have to rename the compounds. So we have many compounds which have the same band structure as cadmium telluride, and we have many compounds which have the same band structure as mercury telluride. Why are this compound interesting? Despite of that, they really show this nice Dirac surface state. They are interesting because here with this ternary compound, we also can have superconduct. So this is simply the real band structure. But since which is here in nice agreement. So we have the surface state here, like in mercury telluride, below the Fermi energy here in this ternary compound. Why are the 3? Oh, now I forgot the slide. But why are these ternary compounds interesting? And I hope that we make some progress now here, because these compounds are also very often superconducting. If they have the band inversion, they are semiconducting, so no superconductivity, even if you dope it to the same electron carrier like in the other case. So this has a superconducting and this has a non-superconducting, which might be accidentally, I don't think so. And they are not non-centrosymmetric superconductors. So still we are working very hard on these compounds to find spin triplet superconductivity in this compound, and there is some evidence already. So seeing that, again, what I said, combining topology maybe with a different properties, similar like you saw in twisted graphene. Also here you can eventually combine the band inversion with superconductivity. So the question is, this is unconventional superconductivity, and then can we go even to more interesting properties, maybe like Majorana fermions. Anyway, you can continue, and I don't want to continue here because I think I don't know how long the time for the questions is, so there is already, but no questions yet in the chat. So since we have here this degeneration of the gamma 8 band, which is not very good, so we can break the symmetry and make topological insulators here by going to tetragonal distorted compound. So Leslie is working on the zirconium silicide sulfide compounds, which are tetragonal, etc. You can go to hexagonal compound, but since in 2 hours I have not the time, so you could read about the hourglass compound, which has the same number of electrons like the Heusler compounds. It's a hexagonal version of some Heusler compounds, etc. But I don't want to bore you with the many different compounds. I want to go a little bit fastly in the next direction. I have to skip eventually this to Hall measurements. So this is what we like to do nowadays. And maybe go back here. So we like to measure our crystals by Hall. So this is a PUP. So we put the crystals, which you have seen before, or maybe also the thin films. We make contacts here, and then we measure the electric current in a magnetic field. This is Hall. If you only measure the current, you know whether it's a metal, an insulator. But if you measure it in a magnetic field, you get much more information. Or you can also apply other external stimuli. Okay, temperature, we always change the temperature, but we can make measurement of light-matter interaction. So most of the experiments we are talking about here, and probably also many other experiments, are use transport measurements with applied external stimuli. So therefore we can have in mercury telluride, which is the diamagnetic semiconductors, and many topological insulators are insulators, semiconductors, and therefore diamagnetic. We measure the Hall effect, but recently, and this is for tomorrow, so we also might investigate magnetic materials. And I told you already, this paper from Haldane talks about magnetic materials, even intrinsic magnetism in materials, which leads to the anomalous Hall effect. And he was talking about the quantum anomalous Hall effect. So tomorrow we will talk about the magnetic topological materials, and first about the classical effect, like here the Hall effect, the anomalous Hall effect. This is an additional contribution to the Hall effect coming from the magnetism, intrinsic magnetism of the material. And then we have the spin Hall effect, which is related to, in paramagnetic materials, it's related to the spins in a paramagnet, and these are all classical measurements. The spin Hall effect most of the time is measured with an interface anyway. So, but all these Hall effects have their counterparts. So like the Hall effect has a quantum Hall effect. This is related to the discovery of Klaus von Klitzing. So he took some simple two-dimensional electron gas, again, gallium arsenic, very similar, like I showed you for von Klitzing, for Molenkamp's experiment for the quantum spin Hall effect, looks very similar. Here, you only need a large magnetic field, which you have to apply to see this topological protected edge states. Again, spin and momentum is locked. We already talked a little bit about the quantum spin Hall effect, where you don't need an external magnetic field, so you get it even without a magnetic field. And then sometime later, there was also discovery in magnetic materials similar to the quantum spin Hall effect. Simply by doping with magnets, you could see the quantum anomalous Hall effect.
Claudia?
Yeah.
Yeah, there are a couple of questions. So the first one is, how can topology help us understand the preference in nature of elements with certain chirality above the other one?
This is the following part. So this is a very good question, Anna. So this is I'm not yet at chirality and I'm not yet at the chiral anomaly. So anyway, so we don't understand it. This is still a big question. Okay, so far we don't understand it, but I have some ideas about this, and this is the ideas we want to work on. So the question is really, how could it happen that we have more molecules of this chirality? Why are we all only molecules of one chirality? So I can simply say I can give you tomorrow a few ideas about this, because I think today I can talk about the chiral anomaly, which will come in the following slides. And the second question is also good. Does the sample growth rate has any? Yeah, Adolfo, you could read.
Yeah, I can read it. Does the sample growth rate have any effect on the final chirality of the compound, or are they always racemic?
This is also a very good question, Anna. So I think in principle, they are. So this is in solids, it's not so easy. So if you look on the quartz crystals, which are chiral on Earth, you might have exactly 50-50. If you do an organic reaction, so you put the molecules in a pot, okay? So you do an organic reaction to get a chiral crystal, they are also always racematic, 50-50. So the goal of organic chemists is to get 50.01 on one side, okay? Then you can amplify eventually and come more to one side. So it's not clear. It's absolutely not clear, but I will discuss a few points also in context of my presentation, which is more, because I think maybe topology can help us to understand this, and also what Adolfo says, so maybe Adolfo should think even more about this, to make the bridge between astrophysics, high energy physics, topological materials, plus maybe chiral molecules and twisted graphene. Okay.
Nothing less than that.
Nothing less than. So we want to solve all the big questions in physics and biology in one shot, okay?
Yeah.
Okay.
Yeah, thank
so,
you.
but in this sense, yes. Please continue to ask questions. I still have a little bit of time. Now you stop me, Adolfo.
Yeah, you have we have 5-10 minutes.
Yeah. Otherwise, I also anyway can take questions for tomorrow or whatever. Okay, good. So the quantum anomalous Hall effect is what we measure if we measure this very complicated device on von Klitzing, and we see these beautiful plateaus. Now you can understand why I was complaining about the lousy plateaus, the first plateaus from Lorentz-Molenkamp, and you see when you have a plateau, the resistance in the other direction. So in one direction you have a plateau, in the other direction you get a zero resistance. And the explanation is this, I'm sure you know, but anyway, so because in a magnetic field, and this is what you need here, large magnetic field, you get this Landau levels. And if you have only one Landau level, and this Landau levels depends on the magnetic field, and if you only have one Landau level below the Fermi energy, so all electrons are in the zero Landau level. If you have more, you see this plateaus, more plateaus. Anyway, and you can see even it in graphene at room temperature. So, and you see also this fractional values. I don't know whether I've shown it. But for me, was very surprising is that what is new is that you can see it even nowadays in single crystals. So this is another interesting open area where Johannes is working on also. So can we have a 3D quantum Hall effect in single crystals? How do we have to design the single crystals? And he even saw some fractional quantum Hall values. So I always say if we would have better low temperature, better measurement at lower temperature earlier, So we would have maybe even found the quantum Hall effect earlier in single crystals. This is zirconium telluride and hafnium telluride, and we didn't need to wait until we have this well-defined samples which von Klitzing had, which enabled him to find the quantum Hall effect. Okay, so anyway, so going then to back to Roald Hoffmann, and what he taught us, despite of all looking for the forbidden crossing, etc., is also if you have one atom in a unit cell, and if you would have one hydrogen atom or one s electron in a unit cell, you would have this very simple band structure, which is parabola. So, but in the moment when you have more atoms in a unit cell, your unit cell is doubled. So in reciprocal space, my Bryon zone is halved. So we fold down the band structure, and then we end up with this. This is a picture from this book from Roald Hoffmann, and we end up with this linear dispersion at the edges of the Bryon zone here. And this is what we exactly call a Dirac cone. This is a picture from Paul Klee, here very nicely showing even 2 Dirac cones, white semimetals, which he already had in mind. And so this is also why this is not very uncommon. So crossing points, which are this linear dispersion in the band structure like we like in graphene, and you heard a lot about graphene, is also quite common because it's a simple features of band structure. The question is the Fermi energy exactly here to see the nice properties in transport, and this is very nicely in a simple band structure, really exactly in graphene. As you can see here, in graphite, you already see that even in the original 3-dimensional case, band structure is not so different, but if you go to graphene, it becomes here really nicely linear. And this is related to the unusual electronic structure of graphene. So we like this linear band dispersion, and here again, the 3-dimensional picture of our overlap between the conduction and the valence band and the overlapping area, which is a line here, for example, a nodal line. Then if we have a spin-orbit coupling, we can have topological insulators, as we already discussed. This picture looks normally different, but it's simply, okay, anyway, sometimes it happens. Or if we have points in the Bryon zone like here, where we have points which are protected by symmetry by rotation symmetry, for example, then we might end up with this linear dispersion, as I showed you before, which is also if you have backfolding of electrons. So of the backfolding of the band structure. Anyway, so if you have these crossing points like here, in the Bryon zone, so this protected points. So this is again interesting because then we have a semi-metal, and depending from whether these points are on high symmetry points or on low symmetry points, they can be in low symmetry points. We even can have chirality here. So which means if we have it in the high symmetry points, these points are falling together, so and are degenerated. But if it's on low symmetry points, or if you apply magnetic field, so these points are, the degeneration is lived, so they have a phase. So the spin and the momentum which is locked on the electrons, so they have different chirality. So this is again, so before we talked about chirality of twisted graphene, we talked about chirality of molecules, but here we talk about chirality of electrons. So in the moment when the spin and the momentum lock, we can talk about chirality of the electrons. And this makes this super interesting because now we have similar like the chirality of molecules, the chirality of electrons. And this can lead to very special properties here, like you maybe already know as a theoretician. So we can have, it's not as nice as it should look here. So we have this in the bulk electronic structure of this material, we have this white points, so-called white points, which act like monopoles. So we have, because of the different chirality, we have also different properties of the Berry phase, and this leads also to this Fermi arc-kind surface states. And this is what I think is super exciting, because so now having chirality in crystal, chirality in molecule, chirality in twisted graphene, and chirality in electrons. Why is this so interesting? Because for white semi-metals, there is this very nice prediction of the chiral anomaly, maybe boring now for Adolfo, but super exciting for me, because this is even described nicely in the Wikipedia, so that because this is a concept which comes even from high energy physics, because what we do, we all solve the Schrödinger or Dirac equation. The Dirac equation, if we have to take into account relativistic effects, and in high energy physics, they do the same as in solids. And in high energy physics, they try to understand the asymmetry between matter and antimatter and fluctuation of the vacuum states and their speed of light. The speed is the speed of light, but they have the same description like we would have, and we have here only in our semi-metals electrons and holes and Fermi velocity. But the same is the case, and the chiral anomaly is in high energy physics. This one possibility to understand maybe the asymmetry of light, matter and antimatter. So far, it's not proven experimentally, also in high energy physics, but still people doing experiments, for example, nowadays on via heavy ion collision, they try to show this asymmetry. And therefore, it was very nice when it could when while semi-metals were discovered, that in while semi-metals we maybe could show as a quantum simulation that we can have eventually this chiral anomaly. But here we more talk about, this is a nice picture from Johannes Stone, more about quasi-particles we in solid, so because our particles get dressed, but it's not like the real chicken, but it still looks like the real chicken. And this, you could say, are really astrophysicists and high energy physicists interested in what we do in condensed matter physics? And indeed they are very interested in this, because this could show them that the fundamental equations are making sense if you see it in model system, and it might be an explanation then to maybe solve one of the big questions, the asymmetry between particles and antiparticles, which is more or less also the origin of our universe. Okay, so I have not the time, but this is also a nice figure of Johannes, where we always have to say it. We have this symmetry breaking in the we're discussing here in topological materials. But if you talk about astrophysics and if you talk about high energy physics, we are dealing with totally different energy scales and also length scales. But still, I think it's very interesting to compare these different concepts. This is so one similarity is like what which is a similar parity violation is the chiral anomaly parity violation found by Wu experimentally in the beta decay of cobalt atoms. So this is it's related to the weak force in the nuclei, which is one way of explaining this asymmetry. And she could show it in the beta decay of cobalt. And there was a theory, unfortunately, she didn't get the Nobel Prize, only the theoretician. So good for you doing theory. Anyway, but it's very interesting here. Also, I show this example because it makes the bridge also. This process, the weak force in the weak force in the nucleus is nowadays even one possibility, maybe to explain the asymmetry between the two chiralities. So this is connected with this guy. He's a professor at ETH Zurich, and he tries really to show that you can make a difference. So if you take the weak force into account, you should see it in spectroscopy. It could lead to a tiny asymmetry, that we get a tiny little bit more from one molecule than the others. And this could be one possibility it could be one possibility to explain even the origin of light. There's a question?
Yeah, there's a question by Mikael. What other theorize the phenomena in high energy physics, or maybe other areas could be realized in condensed matter context? What would you like to see in particular?
Yeah, so I have already some. So you could ask this question also to Adolfo. Thank you, Michael, because Adolfo has given already a proposal, and recently I got another proposal from Jan, so which is more related to optics. Adolfo, we are now able to do optics. You might know because Fabian is now with us. So, and we still dream about the Horizon experiment, and maybe you should talk also. We are going in a very good direction, so we are doing similar things. So we find now more and better ways and different materials. So we have this chiral materials, okay, so which might open new direction, and also the quantum Hall effect, the quantum fractional Hall effect, and things like this might help. Anyway, so this is a very good question, but the question should be addressed to the theoretician. We already have a list of some things, okay? There's still the idea to show with negative curvature the horizon and the black hole experiment. And this is, I think, on the very urgent to-do list of Johannes and us. And yeah, so we are ready to wait for good ideas. Okay, now with the twisted materials, one could even think, can we take twisted materials into account for doing some of this experiment? Okay, I think I'm running out of time, and I think I will start with the Racemic methods and the experimental observation maybe tomorrow. Then I want to go to the axion insulators, and I want to do a little bit of chiral stuff. And if there's time, magnetism, but it might be not enough time. But I think I will give you a little bit a taste of the different direction to inspire the theory to do more. And there's another question. So,
very good. So thank you, Claudia, for the talk. Very inspiring. I'm going to take this other question. It's a clarification. No, okay, maybe this point was explained and I missed it, but let me ask it. Can the presented chemistry-based point of view give a nice interpretation of the obstruction to having an atomic limit in topological insulators?
I have to think about this. The chemistry-based point of view to give a nice interpretation of the obstruction to having an atomic limit and topology. I have to think about this, okay? I maybe need to discuss more with Maya about this. We were already, so I see this different group of obstructive atomic insulators, like the obstructive atomic insulators, and then the filling enforced obstructive insulators. I can explain by the difference. I can explain by chemistry. But can I explain the concept? I think there are some hand-waving arguments in chemistry which simply takes experience into account, but this is a nice way to really bring it on some rational fundament, I would say. So therefore, I think from the fundamental viewpoint, it's not straightforward. But anyway, so it's a very good question. I could give another talk about this. I'm working on this for Maya and Andre. Okay.
Very good. Any other questions? I don't know if Maya wanted to add something to this answer.
No, that I think is something we have discussed that already, Claudia, is that we need to explain the obstructed atomic insulators in terms of chemistry. That was the question, and we are working on that.
Yeah, so we really have to work on this, Maya. I'm working on some slides already, but I think this is not complete. Next year in school. So this year you have to work on new axions, prediction of new axion insulators, guys and girls here in the background. Okay, so you to do is more model systems for energy physics and astrophysics. We are waiting for this. Okay, so you see we have a whole slew of materials. We can even twist and bend and whatever, strain and so on. So now we have optics in place. Okay, so. And I think I want to, and more understanding of the quantum 3D quantum Hall effect.
Very good. Okay, then we're excited to do that. Maybe we can thank you for your talk, and you can tell us more in tomorrow.
Yes. You can have a question tomorrow, right? You can be prepared for questions tomorrow.
Okay, very good. And then I'm going to welcome Christiane Morais-Smith from Utrecht. I think, Clara, you have to probably unshare your screen. Yeah, very good. And Christiane, if you can share your screen.
Do you hear me?
Yeah.
Is the sound loud enough? Is it good?
Yeah, I hear you. Okay.
Okay, very good.
Yeah, so I'll maybe interrupt you with questions as they come along. Okay, great.
That's correct. We are starting 10 minutes late, right?
Yes, I'll take that into account.
Very good.
So the floor is yours, and looking forward for your talk. Thanks for being here.
Thank you very much. So good afternoon, everybody. It's a pity that I can't look into your eyes to realize when you are understanding and when you are not. But I am nevertheless very happy to be here with you and to go on telling you some things about topological insulators that hopefully you have not yet heard. So you have been learning a lot last week and this week about topological insulators, but today I am going to tell you something that probably didn't come yet to your mind. So just as a very generic recap, we have learned that topological states of matter are describing materials that are insulating in the bulk and conducting at the edges, that the edge conductivity is quantized and protected by a topological invariant. And what is very interesting is that the field from the very beginning, since the discovery of the integer quantum Hall effect, and immediately we get the TK and N invariants, this field of topological states of matter developed in terms of symmetries and topological invariants. So immediately people looked at the symmetries of the materials that you have at the dimensionality, and we could get the tenfold weight table that could explain what to expect in terms of topology. And then there were beautiful experiments coming up, and they were always done in terms of transport or ARPS most of the time. So the discovery of the quantum Hall effect by von Klitzing, it was transport. The discovery of the fractional quantum Hall effect by Sturmer was transport. And then when topological insulators came in, we had beautiful experiments with ARPS, looking at how is the shape of the energies and so on. But you wonder, you see, when you come to the university, you will start learning things besides classical mechanics and quantum mechanics. You learn thermodynamics, you learn electrodynamics, right? So every time when there is a new discovery coming up, if you think of superconductivity, when it was first discovered by Kamerlingh-Onnes in 1911 and nobody knew what it was about, the first thing that people tried to do was to use the common theories that we have, like Pippard was doing thermodynamics of superconductivity. And then London was doing electrodynamics of superconductivity. Only then we had more phenomenological theories like Ginzburg-Landau to explain the phase transition, and then finally the BCS theory. But with the topological insulators, we took a completely different route, and we went into symmetries and classification based on the dimensionalities and on the symmetries present. So I wanted to take a step back and ask the question, what about to study the thermodynamics of topological insulators? So one thing is, we know that the Ginzburg-Landau theory doesn't work because we have non-local order parameters, right? But can we still attempt to do some thermodynamic description of TIs? That could be extremely nice. To start with, we calculate invariance at 0 temperature. But we know that if this topological state would only hold at 0 temperatures, we could never measure them because we cannot reach 0 temperatures. So what is the fate of the topological phase if this temperature is non-zero but small? What means small? How large can it be such that I still have the features that I am calculating at 0 temperatures? And then the next question is, if I am able to do a thermodynamic description of topological insulators, do I get any relevant further information that I didn't know yet while calculating the topological invariance, for instance? So those are the questions I am going to discuss with you today and on Friday. And so today here, we are going to discuss how we can do a thermodynamic description of topological insulators, and I will use some old concept, which is called the Ehrenfest classification. So today we are going to analyze 1D, 2D, and 3D systems, which are just the simplest ones that you have already learned in previous lectures, like the Suschriff-Heger, the Kitaev chain, the Kane-Millet model, and the Bernevik-Hughes-Zhang model in 2D and in 3D, and to look for universalities in the behavior of these systems, and to understand what breaks down, for instance, if I get something more complicated like a long-range Kitaev chain, and what can we say from the thermodynamic description. And on Friday, I will go further, and I will then look at the higher order TIs and at the non-Hermitian topological insulators, again from the thermodynamic perspective. Okay, so let's start with the simplest models that you have already learned and you have already understood, and we can set the basis for what I want to discuss. So I told you that I want to describe the thermodynamics of TIs using the Ehrenfest classification. What does this mean? So Ehrenfest, and he was in Utrecht, by the way, in Leiden, and he had an idea that we can classify a phase transition. At the time he was thinking of a classical phase transition. If I look at the Gibbs free energy as a function of temperature, and I start taking derivatives of the Gibbs free energy. So I can take the dg dt, the first derivative or the second derivative, and so on, with respect to some parameter that could be driving my phase transition. And what he found, and he classified, is that the order of the phase transition is given by the order of the derivative of the Gibbs free energy that is showing a discontinuity, like here, it's the second derivative, or a jump or a discontinuity, a divergence, okay? So here you see just the jump is this discontinuity, but it could be a divergence. That's how it has been generalized afterwards. So he would say, if I have a system that is described by a certain Gibbs free energy, such that the second derivative is showing this feature, so this is then my critical temperature, and there is a second order phase transition at this point. So if I would see the jump in the first derivative, it would be a first order phase transition. If it's in the third, it's a third order phase transition. So afterwards, the description of phase transitions became just the first order and the other, which were called continuous from the second on. And afterwards, the notion of phase transitions was much better described by the work of Landau and Ginzburg. But there we had the notion of an order parameter that was local, and there was the notion of breaking of symmetries. But now, when we are talking about topological insulators, there is no breaking of symmetry, and there is no local order parameter. The order parameter is extended, it's non-local. So we can't apply Ginzburg-Landau, but we can still attempt to apply the Ehrenfest classification, which is just to look at free energy and see, is there a jump? Is there a discontinuity? Where? What does it mean? Does it correlate to the things I know from the topological invariants? So that's what we are going to do now. So before we start doing this, we have a trouble, just a more general problem than all that. You will tell me, look, when I try to do thermodynamics, it implies I'm looking at the system in the thermodynamic limit, when the length scales are going to infinity. But wait a moment, I am interested in a topological insulator. So a topological insulator has boundaries, and it's precisely the boundary that's important, because they are hosting either the edge states or the zero mode Majoranas and so on. So the first problem that I already encounter, even if I have an easy classification like the Ehrenfest one that might work, is how to do thermodynamics of finite size systems. Can I do that at all or not? So you start going to the literature, and you will find, yes, others before us have been trying to do that. So if you think in terms of, but it might well be that the standard thermodynamics is not going to work. Usually, the standard thermodynamics revolves around the thermodynamics identity, where the GE is TGS minus PGV plus mu GM, right? And this dictates that the energy is going to be a function of the entropy, the volume, and the number of particles. And in standard thermodynamics, we assume that the energy is linear in these parameters. Okay, so it's extensive in the volume. And then you integrate the thermodynamics identity and you get this expression. But now I am in trouble, because I have a system where the edge and the bulk could be behaving differently. And how do I do that in terms, because now the volume, the bulk and the surface, they are not scaling with volume in the same way. One is volume, the other is surface, or one is length and the other is a constant, right? The surface has a dimension less than the bulk. So how to handle that? Actually, already Gibbs was thinking about that when he was studying droplets. And what Gibbs did, he has artificially separated the bulk and the edge and treated them as two independent systems. So he wrote the thermodynamic identity for the bulk, another one for the edge. He supposed that the bulk and the edge were in equilibrium, in thermal equilibrium, and with the constant mu with the same chemical potential. And then he could come to an expression at the end, where here again you have not only PGV, but you have some gamma GA. This is the surface term, and this is the volume term. Okay, so by getting the two and put them in thermal the same temperature T and at the same chemical potential mu, he came to an expression like this. And again, he assumed linearity and integrated and got this expression. So he could describe his droplets. But we were very hesitant to take that, because to take the bulk and the edge as independent systems, we know at the topological phase transition, the bulk, the edge states are merging into the bulk. So would this be the best approach to use in an attempt to describe the thermodynamics of TIs? So we went on looking at the literature. And then we discovered something very interesting that maybe you have never heard about. And it's something called Hill thermodynamics. So in the Hill approach, he had a completely different way to look at things. There are books about Hill thermodynamics. And the idea of Hill, it's nowadays called Nano Thermodynamics. It's precisely a prescription to handle small systems. So what did Hill tell us? He said the following. It sounds very simple, but it's tricky and it's actually very deep. He said, let's take a huge system which is composed of an ensemble curly N of many small systems which have a certain number of particles, normal N, and volume V. So I have many subsystems, and the number of subsystems is this curly N. Okay? And now I will look at this ensemble of, and curly, I'm putting a twiddle here in my equations, any twiddle copies of the system. So now, when I will have the expression for the thermodynamic identity in terms of GE as TdS minus PdV plus mu Gn, when I do the variation of the volume, the total volume I can change in two ways. One is by keeping constant. The total volume is this curly N times the volume of each small subsystem. So I can either keep the number of systems constant and vary the volume of each subsystem, or I can keep the volume of each subsystem constant and add or take away some of the subsystems. So to vary the number of subsystems, okay? And this term he called P hat to distinguish from the pressure that I had here. Okay, so when he writes that, now he will not assume linearity, that the energy depends linearly on the volume, but he will integrate at constant volume, temperature and chemical potential. And when he does this term is getting away, and you are going just to get just the P hat V times the N twiddle, and the mu Gn, the mu N, and the Ts, okay? And when he does this, after now, he can just divide by the number of subsystems and get the expression for the energy per individual system. So he didn't assume linearity in the volume, and what he's getting here, it's no longer P, but it's P hat. And then he goes on and he says, okay, now I can define the free energy as we do usually, E minus Ts minus mu N, but now instead of having this being equal to minus PV, this is minus P hat V for my new system, right? And I would like to understand how P hat is different from the usual PV that I would have if I would be doing the usual thermodynamics. And this difference that he's capturing here by this chi is what he calls the subdivision potential. So the subdivision potential is going to be the quantity that tells me in which way this P hat that I have obtained without assuming linearity is different from the usual pressure that I would have when I assume linearity. So actually, this parameter is an extra degree of freedom that is characterizing deviations from linearity. And now he goes on and says, okay, the connection with the microscopics will still happen via this Gibbs relation that we had, where our free energy is going to be given by minus 1 over beta log trace exponential of minus beta h minus mu n. So this is something that we know if you have a Hamiltonian, by using the log trace expression and beta is 1 over kBt, I can get my free energy, right? And that is very nice. And he supposes that this is still holding, but this is no longer necessarily linear in the volume. So you are giving up extensivity, okay? You have a more generic theory. So that was very nice. And then at the time, Chamberlain was a student of Hill. So for instance, he used this theory to explain the glass transition in supercooled liquids. And then he used it to look at a mean field description of critical scaling in ferromagnets. And more recently, this was even used to describe very large systems. But when you have gravitation and the interaction decays slowly, the Hill thermodynamics still applies, even to describe cosmology. So that's the theory that we thought could be appropriate to use here, because then we are able to take into account the different dimensionalities of the bulk and edge. Okay, so what we are going to do here, we are going to do the following. So we will make an ansatz that we are able to describe, to use, to create a thermodynamic potential for our system in terms of temperature, chemical potential, and volume, which is going to have a term. The first term, I hope you can see my mouse. Do you see my mouse when I'm turning here? Or should I take a laser pointer?
Yeah, we see it.
You see it, okay. So you see this first phi, I am using capital phi for the total. And now here I have this phi, which is for the bulk. And I am dividing by some area times W, which is a length scale. So area times the length scales gives me volume. This would be the phi for the bulk. And this is the phi for the surface, because it's multiplied by the area, okay? So I will make an ansatz that I can separate my total thermodynamic potential in one part from the bulk, another part from the surface. And now this part, the total, I can calculate numerically, because you remember here I have, I have a Hamiltonian. So if I have a Hamiltonian, I can calculate the total phi. And now I will attempt to separate which part of it is from the bulk and which part is from the surface. So what I can do a linear fit. I can calculate this phi for different length scales, and then I can immediately see which part is scaling linearly is the bulk and the part which is constant is the boundary. And that's what we do. So we will take that the total phi is the bulk times L to G and the boundary L to G minus 1. And then you will take a certain model, a certain Hamiltonian. You calculate the thermodynamic potential or the free energy for several length scales. You will see there is a large part that's scaling linearly. This part is from the bulk. And there will be something that's almost invisible here, very tiny, which is from the boundary, okay? And you will see that in your attempt to do this linear scaling, if you are far away from the critical point, the spreading that you have is in 10 to minus 14. So it's quite good, but this error gets more important, 10 to minus 9. It's still very small when you come close to your critical point. Okay, but it's possible to do that. So let's then do it to some very concrete example that we have already learned and see what we get. So let's take the Kitaev chain. So it's a one-dimensional, describing a one-dimensional spinless P-wave superconductor. Oh, sorry. So we have here the chemical potential and the hopping term from site I to I plus 1, and the pairing delta that is describing the pairs of electrons that are paired in the nearest neighbor sites, I and I plus 1. Okay, this should be I and I plus 1. So we do a Bogoliubov transformation. You see that the Hamiltonian in K space looks like that, right? And then you know, you have already learned that there are two phases. If the modulus of the chemical potential is bigger than 2T, we have a trivial phase with a trivial gap. The pairs are made in that way. But if the modulus of mu is between plus 2T and minus 2T, I will get a topological phase where I will get Majorana edge modes for the eta 1 and the gamma n, right? So this is what we already know based on the topological invariants that we have been studying before. So let's now see what this thermodynamic description has to tell us. So you take this Hamiltonian for the Kitaev that was here, you put inside the trace formula, you do the scaling analysis as I have shown, and you separate the thermodynamic potential for the bulk, which is in red, and for the boundary, which is in blue, phi 0 and phi c. Okay? I'm showing you plots that were done for mu equal to 2t equals 0.5, so delta and t are 0.25, and these results are at 0 temperature. So once I have my boundary and my bulk free energies, I can now take derivatives of them. And that's what I'm going to do here, the derivative of the free energy with respect to the chemical potential. So my thermodynamic potential at t equals 0 is nothing but my free energy. And now I immediately see something. Phi prime c has no features, but the phi prime 0 has a discontinuity, has a peak. So from here, according to the Ehrenfest classification, I can immediately say that the phase transition at the boundaries is occurring at mu equals 0.5, and it's first order. Now I take the second derivative. When I take the second derivative, I see that now the red, which was the bulk, has also a discontinuity, has also a peak. So from here, precisely again, at mu equals 0.5. From these plots, I can conclude that there is a phase transition occurring at mu equals 0.5 for the bulk and for the edge, but the order of the phase transition at the boundaries is first order, and at the bulk is second order. They occur at the same point, but they have different orders, okay? So this agrees completely with what we knew from the topological invariant, because from the topological invariant, we knew that, so for mu larger than 2t, and now here, we know that the 2t, mu equal to t is precisely at 0.5. We knew that there was a topological phase for mu smaller than 0.5 and a trivial phase for mu larger than 0.5. And what this thermodynamic description is telling me is the point of the phase transition. But how can I know which phase is which, right? Because the topological invariant tells me the Berry phase and this topological invariant is going to be 1 or 0 in the trivial and non-zero in the topological. But here, I don't know. But we can go further. So just recapitulating, because that's the main message here. For this Kitaev chain, the phase transition at the boundary is first order happening at mu equals 0.5, and at the bulk is second order happening at mu equals 0.5. Okay? So, but what else can I say about it? And I did these calculations using this linearization. Could I have done these calculations in a more elegant manner using something else? Actually, yes. Actually, we could have been using Green's functions and calculating correlation functions, because these would be much more economic to do numerically. Before, what I was calling phi, now I am calling omega, because each student in my group is completely free to call the free energy by the letters that they like. and then I am in trouble when I have to show you the slides. So capital omega now stands for the capital phi, and the little omega now is going to be the density of the thermodynamic potential. And I can now rewrite in a very easy way in terms of correlation functions or Green's functions if I take the derivatives directly. And now I can then calculate the Green's functions and get the derivative at the edge plus n, which is the number of particles times the derivative for the bulk. And you can see that if I use this type of procedure, in red is the procedure using this correlation method, and in blue underneath, you can't even see the difference, was the scaling method using the linearization I have shown before. And here you see again the topological phase transition at mu equal to t, because t is equal to 1 with the two methods. So I could do calculations using correlation functions. Okay, but now that I have a thermodynamic potential, I can calculate more things that I couldn't do before with my topological invariants, right? I can calculate entropy, heat capacity, density of states, all these beautiful physical quantities that we know from thermodynamics. So we just need to take the derivative of the thermodynamic potential with respect to the temperature, and you invert the sign and you get the entropy. So let's see what we get for the entropy. Look how beautiful. What should I expect to get for the Kitaev chain if I look at the boundaries? The boundaries, I have two Majoranas, right? So I should get log 2. And that's precisely what I get for my entropy. This is the blue for mu equal to 0.3. And we will now start doing these calculations as we go across the topological phase transition, that is mu equals 0.5. So look at that. We know that the entropy should be log 2. And now when I calculate the entropy from my thermodynamic potential as a function of temperature for finite temperatures, how long should this topological state be robust? Well, it depends on how close or how far I am from the topological phase transition. For instance, if my chemical potential is 0.3, I am far away from the topological phase transition, which is at 0.5. Look, I can keep increasing temperature here. Temperature, kBT, is measured in units of energy, that's the hopping T. And look at this curve, it remains at log 2 up to pretty good temperatures, and only then it starts deviating. So my topological phase should be robust up to pretty good finite temperatures. But if I come now to mu equals 0.45, it starts going away from log 2 already faster. And if I am at mu equals 0.49, very fast, it's starting going away from log 2. And immediately after I pass my phase transition at mu equals 0.5, look at what happens to my entropy of the boundary at mu equals 0.51. It's becoming negative. So you will say, very strange, right? Well, in red, you have the entropy of the bulk. That's much, much larger. So the entropy of the bulk is growing linearly here. You can't distinguish much the values for the different values of mu. But the total entropy is still positive, as it should. But locally, the bulk and the boundary are acting as different thermal machines. One is going to be a refrigerator and the other is going to be a heater, okay? And you see it already in the different sign of the entropy. And this is very interesting because if you want to build any thermal machine, close to the phase transition would be the point where you would have the best profit in any kind of cycle that you could be building. There is a question.
Indeed, there is a question. Can the red and blue lines be measured separately in an experiment?
Yes, you would need to tune the chemical potential. So if you are able to design any experiment where you can tune I was thinking about moving the mill. Yes, so you need local probes, right? How can we get local probes? That is very difficult. Thermodynamics didn't progress enough in terms of experiments to be able to separate. But when I go now for the density of states, that I can measure with an STM, and an STM is a local probe, and then I could measure at the bulk and at the edge separately. For the entropy, it's a bit more difficult. It's still a challenge for experimentalists. And it would be very interesting if experimentalists would start thinking about that. How to design setups to measure experimentally thermodynamic properties like heat capacity and entropy separately at the bulk and at the edges. There were some measurements attempted by the group of Paglione. He was measuring samarium hexaboride. And what he was doing, he was taking a certain sample that has a certain area and a certain volume, and then he was smashing it. And when he smashes, the proportion between the volume is the same if he doesn't lose too much into powder, but the ratio between the volume and the surface increases because you smashed into many pieces, so you have much more area, although you have the same volume. And he kept doing so to try to understand the importance of the surface in comparison to the volume. But it would be much better if more appropriate tools would be developed to independently measure bulk and boundaries. Are you happy with the answer, or do you have any other question?
There is no more questions. Maybe we can.
I can go on.
Give it as answered, and if there's a reply, I'll let you know.
Yes, if there is anything else, you can just ask further. Very good. Okay, so that is for the entropy. Now we can calculate the heat capacity. The heat capacity now is the second derivative of the free energy with respect to the temperature, right? And now for the Kitaev chain, the Kitaev chain is a conformal theory at the phase transition. And we know that for a one-dimensional conformal theory at low temperature, we know the expression for the heat capacity. So first of all, we calculate via the derivative of the free energy that we had. We get the red curve. But now we can compare this red curve to the theoretical predictions that we have from conformal field theory. And that is this blue curve here. And from here, I immediately read out that my heat capacity is pi kBT over 6. And this tells me that my central charge is 1/2, because this is in units of kBT over h bar v equal to 1. So this immediately allows me to read the central charge, and I say, great, my theory is correct. That's the central charge I should have got. There is another question.
Yep, there's another question. Is there a reason that the Kitaev chain was chosen as an example over, for example, the SSH model?
I will get to the SSH model in 1 second. I just took one of them that you have already learned, and now it's precisely the question. Before I get into the SSH, let me tell you, it's 3 or 4 slides, and I will show you the results for the SSH. No, there is no reason. Actually, I will show you results for all of them, okay? Very good, and everything should hold the same way. So now, you see, I am telling you thermodynamic properties as a function of temperature. So that's very nice. It tells me that maybe I can look at generalizations of the topological invariants for finite temperatures. And actually, there are theoretical proposals about that. And this goes in terms of something that's called the Ulman phase. So the Ulman phase is a finite temperature generalization of the Chern number. And this is a series of works done in the group of Martin Delgado during the PhD thesis of Oscar Vihuela, and you can see a series of papers for the 1D and for the 2D case. And then there were some discussions about the validity in 2D, but in 1D, things are very well defined. So they have to now treat, instead of pure states, they have to treat mixed states and to calculate the density matrix. And they get a generalization of the Berry phase with the Ulman phase. Yes, there is another question, please.
What about response functions? If the phase transition in bulk and boundary have different order, does this mean that we can distinguish latent heat hysteresis depending on the order of phase transition?
Yeah. Yes. So if you could wait a little bit, I will answer your question with the rest that is to come. I just don't want to short circuit because I have to explain you more things until we get there.
Perfect.
Yes. Thank you. Okay. So there is a way to define a Ulman phase and a topological invariant at finite temperatures. What can we say about finite temperatures and topological invariants at finite temperatures? So we can do the following. We can now look at the first derivative of the boundary and at the second derivative of the bulk, not at zero temperature where I had this very sharp spike, but at finite temperatures. And I keep increasing temperature and I get these red curves that are growing up here and these blue curves that are growing up here, okay? And now you can say, okay, this looks pretty much like response functions. If you think, for instance, at the susceptibility, when you are measuring charge density wave transition. If you have a one-dimensional system at zero temperature, your susceptibility is going to show a very beautiful spike. If your system is not truly 1D, it will be more like a bump. If it is not truly zero temperature, but finite temperatures, it will be like a bump. But it is still a signature of my phase transition, not just as perfect as it is for the precisely theoretical case, right? So we can say, okay, can we attempt to associate some phase transition to these points? And then you will ask yourself, which points should we take? Should we take the minimum point where I have my phi c here that is moving slightly to the left? Or should I take the inflection point, because this is a curve looking up, this part is still looking up if you look here, and then it's looking down. So there is an inflection point, right? The inflection point is not moving away from 0.5, but the minimum is moving away from 0.5. So let's try to trace the minimum of this curve where this kink is, okay, for the bulk. When we do this for the bulk, so we will get a red curve. I'm plotting temperature versus to mu versus hopping. I get a red curve in the places where you don't see this red surface. It's because it's overlapping with the green one. So the green is the curve that was obtained by Vihuela and Martin Delgado in the case of the calculations of the Ulman phase for the Kitaev chain. And our red curve is precisely on top of it. And the only thing we are doing is tracing the minimum of this response function as we move away from zero temperature. So that's quite amazing because we don't need to evoke anything. All the problems that they had with their Ulman phase about not being a holonomy and so on, there were some discussions and some people were contesting their results. We are out of that. We have very clean hands. We just take derivatives and look at the minimum, right? So that is very nice. So until now, I only told you about the Kitaev chain. Now, someone was asking about the SSH model. Now I can have an SSH model with hopping T and T2 for the intra-unit cell hopping T and inter-unit cell hopping T2. I can do precisely the same things, and I will just show you some of the results for the non-extensive part and for the extensive part, which is the bulk, right? So the bulk is going in red, and the boundary is going in blue here. And now again, as for the other one, the first derivative will show a spike for the boundary, and the second derivative will show a spike for the bulk. So for the other 1D model that we have, we get precisely the same features. Another thing that is important to observe is that these features appear independently of the parameter with which I am taking the derivatives. I can take derivatives with respect to different parameters that could be driving my phase transition, and I would see the same result. There is another question. Let me interrupt.
So the question is, why would you calculate the Ulman phase rather than calculating the Chern number? Quantum Hall effect phase should be stable as long as KBT is less than the gap.
Yes. Exactly. As long as KBT is smaller than the gap, that is right. I would agree with you, but it's nice to check, right? KBT is smaller than the gap, so you are inside the gap. You have some fluctuations. How are your fluctuations? It depends on how close you are to the critical system, because of course, as you get closer and closer, your gap gets smaller and smaller. That is true, but you get much more quantitative results if you do that. As for instance here, I can show you, I can extract the central charge of the heat capacity by doing calculations at finite temperatures. It is always very useful to understand how is the behavior at finite temperatures. The intuition that you simply should have KBT smaller than the gap is more like an order of magnitude. But understanding how it really behaves as a function of temperature is more than that. And I think the interest with the Ulman phase is generically already very beautiful, because you are getting a theory that applies for mixed states. It's a generalization of a theory for pure states. And I think it's very interesting. It's my personal opinion. Maybe you find it's unnecessary, but it's just my personal opinion that it's interesting to generalize the concept. Okay, very good. Okay, so the SSH also applies. And then let me recapitulate. We get for the SSH and for the Kitaev, first order phase transition at the boundary, second order phase transition at the bulk. But now we could look at models in higher dimension. Is this going to be always like this? First order for the boundary, second order for the bulk? What if I go to the Kane-Meillet or to the Bhz model in 2 dimensions? So let's take the Bhz model in 2 dimensions, okay? You have the Berneville-Hughes-Stank. You have already learned this model, I am sure, in the previous lectures. And now you know that M is this mass gap. And if M is negative, the system is trivial. And if M is positive, the bands have inverted and you get topological states. And now you can use the same formalism and analyze the system. What do I get if I now use this Hamiltonian to calculate my thermodynamic potential? So on the top, I am showing you the results in the trivial phase, M positive, and in the bottom, I am showing you the results for M negative, topological phase. Now, I am sorry for that, but now the blue is the bulk, and the red is the boundary. It's just to confuse you with respect to the previous, but as I said, each student uses different color codes and different letters for the thermodynamic potential. I'm very sorry for that, but maybe it keeps you awake. And here, this blue curve has been lifted just for clarity by 0,1. So this is 0 for the bulk, okay? So in the trivial phase, you will see that between -1 and 1 for mu over m. So this is this region where I have the gap, I have 0 for the bulk, I have 0 for the boundaries. Here I have some contributions that are coming from the nonlinearities. And when this is the density of states that I am showing here. And if I calculate the heat capacity or specific heat, it is vanishing linearly here, okay? You can see now it's vanishing in that way in the trivial phase. But now I can calculate the density of states in the topological phase for m equal -1, for instance. And again, now the blue curve has been shifted up from 0. This would be 0. So in this regime, the bulk is gapped. It has 0 density of states. But look now at the edge. The edge has a finite density of states. And this is precisely the topological phase between -1 and 1. So when I calculate the density of states, and the density of states can be measured locally with STM probes, I could go to the boundary and measure, and I could go to the bulk and measure. Here I can detect, using a probe that is thermodynamic, that I have a topological state with a finite density of states at the boundaries and 0 at the bulk. Okay? And here, moreover, again, for the heat capacity, I can look, and I know again that this is given by a conformal field theory. And this linear, this linear curve here will show me the value of my central charge that I can obtain from CFTs and validates my theory. And I get that the central charge here is 1, as it should be. So it is very nice. It agrees with all that it's known from other types of theories. But now look at that. What I obtain is that the phase transition for the bulk is going to be second order. That's what is here. So the first derivative for the boundary is not showing any phase transition, is the second derivative of the thermodynamic potential that shows a spike. And the bulk, the second derivative is here, doesn't show anything, it's the third. So now for two-dimensional systems, the boundary is second order and the bulk is third order. It has changed, okay? So we could now do also the Kainin-Meillet model, and I will find the same result, we did it. Second order for the boundary, third order for the bulk. And then we can go to the three-dimensional Bhz model, and I am going to find third order for the boundary, fourth order for the bulk. So there seems to be some universality in the phase transition, and the phase transition is always going to be order G in the boundary and order G+1 in the bulk. So that's what we get out of all the models that we investigated. And the question is, can we understand why it is so? Actually, we can. Actually, there is something that's called the Josephson hyperscaling relation for quantum phase transitions that tells me that the order of a phase transition is given by 2 minus alpha, and this is given by nu times G plus Z. So nu, Z, and alpha are critical exponents, and G is the codimension of the system. So how is alpha defined? If I have a certain free energy that is being driven, a phase transition, a quantum phase transition that is driven by a parameter V, and VC is the point of the criticality, if I see how F scales in terms of V minus VC over V, it goes with this exponent 2 minus alpha. And this is, if I take 2 minus alpha derivatives, I would get then the divergence. And the nu and the Z, they are determined by seeing how my gap is scaling. If I look at it, I position myself at this critical parameter point, and I look how it scales as a function of K. The exponent here is going to be the exponent Z. And if I look at how the gap is scaling at K equals 0 as a function of the parameters V, the exponent here is going to be nu Z. So just to recapitulate what I just told you in the previous slide, close to the phase transition, I can define two parameters. One is the momentum P, that is how far I am from the critical K. And the other would be a letter G, that's how far I am from the critical parameter. That could be V, could be hopping T or whatever, right? And then I will see that the correlation length is scaling with this G to minus nu, and the gap is closing as P to Z if I am at G equals 0, or as G to nu Z if I am at momentum 0, at the critical momentum, where this nu, Z, and alpha are given by this Josephson hyperscaling. And then it turns out that all these models that I have been telling you about, the most common paradigmatic models in 1G, 2G, 3G, like the SSH, they all have nu equal 1 and Z equal 1. So when I look at the order of the phase transition, which is 2 minus alpha, nu is 1, it is going to be the codimension plus 1. So if I am in one dimension, I will have a second order for the bulk and first order for the boundary, because the boundary, the dimensionality of the boundary is 0. G is 0 at the boundary, okay? So that's why I always have G plus 1 and G is 0 for the boundary and 1 for the bulk, or 1 for the boundary and 2 for the bulk if I am in 2 dimensions, or 2 and 3, etc. if I am in 3 dimensions. So all these models can be cast in the Dirac model universality class. This was shown by Rodrigo Aroca more recently. So we can understand all the results we got. Let me just go in my last 10 minutes into something that's quite interesting, that shows also the generality of the results that we can obtain. Until now, I told you about the Kitaev chain, but we could look at a particular case of the Kitaev chain, which is the long-range Kitaev chain, where now, instead of getting pairing at nearest neighbors I and I plus 1, as we had before, we could get pairing at neighbors J and L, which could be at any distance, okay? And we will consider that this pairing is getting attenuated by 1 over J minus L. J and L are the sites which are interacting to form the pair, to the power alpha. So let's now understand how this changes the features of my model. It's fascinating. It's a very small difference. I'm just not making my pair in the nearest neighbors, but I am allowing to get this pairing at higher neighbors. So first of all, when do we retrieve the short range Kitaev chain? It's not for alpha equal 1, because if alpha is 1, I have the same strength, this is not decaying, for all J's and L's, okay? But if alpha is infinity, this term will drop and will cut off all the pairings except when J minus L is equal to 1, because 1 to infinity is still 1. So actually the short range Kitaev chain, when I don't have this term here, and I have J and L distinguishing by 1 lattice site, so L is J plus 1, this will only hold for the alpha equal to infinity when I cut off all the other pairings. Okay, is this clear? And now something that is very interesting that is also occurring here is the following. If I take this system and I now calculate the spectrum of energies, I will see that in addition to this EK squared, which is minus mu minus 2t cosine k that we had before, we have this plus 4 delta squared, this f alpha squared of k. And this function here is a function that is becoming discontinuous when my alpha is going to be smaller than 2. And sorry, this function becomes discontinuous when alpha is smaller than 1. And its derivative becomes discontinuous when alpha is smaller than 2. So this is something that's going to cause lots of trouble, okay? But also I can immediately see when I look at this spectrum that this function is going to cause me more trouble at certain points of phase transitions than at others. Look at here. We knew that mu equal to 2t plus minus 2t were points of phase transition, right? For the Kita-F chain, for the short range. So for k equals 0, if my mu is equal to plus 2t, my energy is still finite. It will be minus 2t cosine of 0 is 1, so it's minus 4t. So ek squared is some value that is regularizing this function here. But for mu equal to minus 2t, this becomes now positive, this is negative, this energy vanishes at k equals 0. So at k equals 0, this first term vanishes, and I just have this function f that is exhibiting discontinuity. So this is the point where I expect to get some mess. And indeed. Now you calculate the spectrum for the finite long-range Kita-F chain. And if your alpha is infinity, you have the short-range Kita-F chain. You see the topological phase here with the Majorana zero modes between -2 and 2. If you come down to alpha equals 3, things are still very well behaved. But now, as I keep lowering alpha below 2 for 1.3, look at what happens. My gap is still closing at this point where my energy is still finite, the EK, right? So the FK, that function, can't do too much harm there, but here it can. Here it is harming, and it is gapping my spectrum, and it is gapping my Majoranas. So my Majoranas are getting gapped and they become a massive fermion. And if I come below 0.5, this phase where I had some robustness of my Majoranas here, below 2 up to close to -2, is completely gone. I start gapping my Majoranas immediately after this point, mu equal 2. Okay, so what is going on here? You can understand, and it's quite nice. So actually this function, f alpha of k, look at how it is. If my alpha is 3, this function, as a function of k, is behaving like this blue curve. It's well behaved. If my alpha is 1.3, look, it is getting very steep here. And if it is 0.5, it is discontinuous. You can also see here what this implies for the energy. For the energy, for alpha equals 3, I have the blue curve, but then I start having this very horrible red curve for 1.3 and this divergence at 0.5. These results are also visible when I look at my winding numbers n. If I write my hk in terms of n of k winding numbers, scalar sigma. For the short range Kita-F, I have a very beautiful winding in terms of NX and NY, okay? NKX and NKY. I get a complete winding, as you can see here. But if my alpha becomes smaller, if I am getting a longer range pairing, look, I start getting sparse points in my winding. And when I come to 0.5, my winding doesn't close anymore. I am getting anomalies here. Look how beautiful this is. So my topological invariants are becoming ill-defined. Well, the bulk and boundary are also behaving differently here because of these long-range interactions. So for alpha larger than 2, I see the usual short-range Kita-F chain. For alpha smaller than 1, I get this massive non-local Dirac fairness because I started gapping my Majoranas. And for alpha between 1 and 2, I get this ill-defined winding number when I expand around k equals 0. And for the edge, it is similar to the short range down to 3/2. So let's look now what we are getting here. It's fascinating, look at that. So for the mu over t equal 2, I get a phase transition. So I am plotting alpha. Alpha tells me how long range is the pairing. as a function of mu over T. And the colors, the difference in colors, the contrast tells me I have a spike. So this signals a phase transition. Everything what is below alpha 0.3 here, I have no precision. You shouldn't believe what is in here, because you have to go to very, very large systems to be able to say something here. So look at this graph down, up, down to this dashed line. So before I had a phase transition for alpha equal infinity between -2 and 2. Here was my topological phase, and here I had a trivial phase. So I see now that for the entire regime of alpha, the phase transition at 2 is well defined. But the phase transition at -2 is stopping. What I'm plotting here is the second derivative of the bulk. So it's a second order phase transition in the entire regime, and here it's stopping, okay? Actually, we could show analytically that the order of the phase transition here in this regime between alpha equal 1 and 2, it is increasing as a devil staircase. So it is second order for alpha larger than 2, but between alpha equal to 3 over 2 and 2 over 1, it's third order. Between alpha 4 over 3 and 3 over 2, it's fourth order. Between 5 over 4 and 4 over 3 is fifth order. And it goes to infinite order as you reach 1. So it's a very anomalous behavior. Moreover, we can look also at the boundary. That is what we are seeing here, the first derivative of the boundary. And again, at the boundary, we see a sharp transition here. That's first order at 2. And at -2, mu equal -2, it is also stopping here somewhere. So we can look again in different cuts how these things are behaving. And we see for 3, we have very sharp phase transitions at -2 and 2. But for 1.3, this became smooth, and 0.5, 2. Here you see that for the boundary, it's still some bump, but then for the 0.5, it becomes smooth. Here you see the correlation functions between the Majoranas at 1 and n. And you see up to 1, you can see something, and then this thing is fading away. But what is very interesting is it looks like a critical endpoint in my phase diagram. Do you remember the phase diagram of water? That between liquid and vapor, I have a critical endpoint because I'm not breaking any symmetry. And after a certain temperature, I can't distinguish liquid from vapor anymore. Here, I have a topological quantum phase transition that seems to have the same kind of features. I have a critical endpoint. And then you can wonder, can I go from the topological phase, which is here between these two lines, to the trivial phase without crossing a topological phase transition by going into a regime in which the topological invariant is not defined at all? And then I circumvent it. These are very interesting questions to be thought about. Let me then come to my conclusions. I have been telling you that topological states of matter can be described by thermodynamics, that the order of the phase transition is universal, and it depends on the dimensionality of the model for most of the models that were studied, like the Kita-Evans, Sushriff-Higger in 1 dimension, Kane-Melee and Bhz in 2 dimensions. I didn't tell you about the Kondo-Ti in 3D, but we did it also. And it is always order D+1 in the bulk and D at the edge. We can understand this based on the Josephson hyperscaling relation and looking at critical exponents. For the long-range Kitaev chain, the bulk and the edge, they decouple because of these long-range features, and the behavior is more intricate. The order of the phase transition increases as a staircase. One very important thing of our calculations is that this method doesn't depend on correlation lengths. So we can describe critical systems. We have a tool that's simple and extremely powerful to describe systems at criticality. And we don't even need to evoke correlation lengths, okay? And moreover, we have a tool that allows us to describe features at finite temperatures, which have been shown to agree very well with the systems in 1G, which were calculated in terms of the Ulman phase. But again, we don't need to enter into any discussion of the Ulman phase being a holonomy or not being a holonomy. We have a very straightforward and simple way to do that. So it looks like that our efforts paid off by trying to calculate thermodynamics for these systems. So here are some of the references where you can read more about all that. These are the simplest examples that are all within the Dirac universality class that I have been explaining you. And on Friday, let me first show you the heroes who have been doing all this work. Anton and Emilio did the first work. They were setting the basis for all that in 2016, doing the Bhz in 2 dimensions. Then Sander Kempkes, together with Anton, he did his master thesis investigating the universalities and looking at all the other models and finding that they were all in the same universality class. Peter Katz did the long-range Kitaev chain, and Iete did the Kondo, the samarium hexaboride Kondo topological insulator. So in the next lecture, I will show you now what can we say if you have a higher order topological insulator and what is about the thermodynamics. And then I will show you also something that's quite intriguing, that if we try to do thermodynamics of non-Hermitian topological insulators, we are going to have fractional order topological phase transitions. And this will bring us into something that we have been studying a lot recently. What about fractional derivatives, fractional integrals? I will tell you more about that on Friday. So thank you very much for your attention. And I think that there are some questions. I have seen already one.
Yeah, there's maybe time for one question, which I'm going to read. So great talk. 2 questions. Great talk. Does the Ulman phase treatment let us use the concept of topological bath, if that makes sense? And which advantages, theoretical and experimental, would that give us?
Very, very interesting question. I don't know the answer for the Ulman phase, but I will tell you about bath when we talk about the non-Hermitian phase. Because of course, any non-Hermitian model can be written as a Hermitian model of a system coupled to a bath. And you can now trace out your bath and obtain a non-Hermitian Hamiltonian, which is going to give us this fractional order topological phase transitions. So I will show you an explicit example where we derive the topological non-Hermitian model out of the bath using Calderon-Leggett. And using the Lindblad formalism, not the Calderon-Leggett. The Calderon-Leggett one is not yet published. And I don't know the precise answer for the Ulman phase, but I suspect yes. Because if you were talking about the density matrices, you could immediately think of it in terms of a bath. But I don't know if this has been investigated or not. Maybe you could check the literature by Martin Delgado, and if not, it could certainly be a great project to look at. Yes.
Okay, great. Then maybe last question. I think that the hyperscaling relation breaks in 4D. Have you computed what would you expect for the order of the bulk and boundary transitions in a 4D model, or maybe in a topological dynamic of phase transition in 3+1 dimensions?
Oh, I didn't. We only went up to 3 dimension. So I don't know the answer to your question. We stayed only with the models that were the most realistic ones. And we only went up to 3 dimensions. We did 3G for the Kondo samarium hexaboride. And we also did a 3G Bhz model, but never to higher dimension. I am sorry, I would not know how this would be, whether it would hold or not. But of course, there are works for the quantum Hall. It would be interesting to look for quantum Hall, and there is the quantum Hall effect in 4 dimensions. That would be a natural model to look at if you would be willing to investigate that. It could be very interesting, though.
Maybe I have a quick question. Do you think, so this thermodynamic approach to invariance, do you think it would work for interacting systems? And have you thought about this?
Yes, we did. So actually, I didn't show it here. Yeah, I have a few slides here. So for the condo topological insulators, these are interacting systems, okay? So we are still doing a mean field calculation, but it is a very elaborated mean field with a 10 bands model, and you have to recalculate the gap numerically every time because it keeps changing in terms of parameters and so on. And for instance, we have calculated the heat capacity also here and calculated, now I don't have these results, but in the paper you can find. And we calculated also the critical exponents, and you can show perfectly that it's nu equal 1 and z equal 1, and it's in the same universality class as the other direct models. And this is an interacting GF electrons. So here we were actually looking for a system where we would not get a direct model with nu equal 1 and z equal 1. And we thought, okay, let's take one with interactions, but it was still the same universality class.
Mm.
And
So, yes.
could it work for a MOT insulator?
I don't know. So we found now systems which don't belong to the same Dirac universality class, and which is going to be the non-Hermitian Dirac universality class. And this is what I will show on Friday. So for a MOT insulator, yeah, I don't know. So I would be reluctant to give answers that are very generic. I would investigate each model and see the peculiarities, because there are several things that are able to break the universality class. So you have seen, for instance, the long range in the Kitaev chain was able to break. You will see next week that the non-Hermitians are going to break the universality class. So each case is one. It was mostly for me surprising that all these models that we are dealing with are within the same universality class.
Mm.
That was more on the other side.
Okay, very good. Thank you for a very interesting talk. I think there are many questions. And maybe we can reconvene at 10 past. So that's 15 minutes from now. And yeah, see you tomorrow for the next lecture. Thank you.
Okay, thank you. Bye.
Bye.
Hi, Cecile. Then passed.
Hi.
Hello.
Okay. So a few minutes from now then?
Yeah, we were running a bit late. I think we said 10 past.
Yeah, 10 past.
Sounds good.
1 minute. You can start sharing your screen if you want.
Sure. All right.
Yeah, looks good.
Good.
Okay, I think we can resume. Before I introduce our next speaker, I'm going to remind everyone that there's a Slack channel for posters. Please check it out, comment on the posters, ask questions, and yeah, interact in general. I think everybody would like their poster to be read, so just check them out. And our next speaker is Cécile Rebellin from the CNRS in Grenoble, and today she's finishing her lectures, and we're looking forward to the the final ending of the story. So the floor is yours.
Okay, thanks, Adolfo. All right. Well, hi everyone, and thanks for joining for this this last lecture of the series. So today is going to be a little bit different from the first two lectures because I'm planning on focusing a little bit more on technique, a little bit more on numerics, but mostly from the point of view of how you can use numerics to well, to see if you might have a fractional quantum Hall state as a ground state in your system. So that's definitely applicable to Rare systems. And in fact, I've already shown some of this numerical data, but I'm going to go into a little bit more details, and I'm going to explain a little bit more how we do this. And before I go into that, I would like to acknowledge the the people that I've had the pleasure of working with on this Moiré superlattices, especially Senthil at MIT and grad students in his group, or former grad students in his group in some cases, Ji Wandong, Yari Zhang, who's moved on after that to be a postdoc at Harvard, and Jenny Crawford. So yeah, this is just a short reminder of the overall outline of the lectures. We started, overall we talked about correlated insulators in Moiré superlattices, both at integer and fractional filling. And today is going to be focused on fractional filling fraction, and more specifically fractional hole conductivity. By looking at numerical signatures of fractional quantum Hall phases, and I'm using that term in a broad sense, meaning it doesn't have to be in the continuum; it could be on the lattice as well. So this is the outline for today. So again, I'd like to start with some motivation. So I've given lots of motivations, I think, to work on these phases of these fractional quantum Hall phases, but I'd like to talk about them in the broader context of topological order a little bit, as it is a very important physical aspect of why we're interested in these phases in general. And then I'll talk about two types of ways of diagnosing fractional quantum Hall states numerically, mostly through spectroscopic methods, from the degeneracy of the ground state and quasi-Hall excitations on the torus. So that's a method that mostly applies to exact diagonalization. And finally, through the edge spectrum. So that's a method that applies in various contexts, but especially well in the context of GMRG. And you don't have to know anything about these numerical methods to follow the lecture. That's I'm not going to be basing the lecture much on technique, really. So topological order. So what do we mean when we say that? So broadly speaking, topological order corresponds to an incompressible quantum phase or a gapped quantum phase. And I'm going to focus exclusively on two-dimensional phases. And I'm starting with that definition because so it's going to be much more specific than that, of course. But I'm starting with this because it's important to distinguish topological order from the concept of a topological phase in general. So topological order is a form of topological insulator in the sense that there is no local order parameter that would help you characterize this phase. But it is distinct from a topological insulator in the topological band point of view, because when you have a state that has topological order, you cannot write it as a product state in any single particle basis. So, for example, a Chan insulator doesn't have topological order in that sense, because you can write it down as a product state, meaning as by just filling up a Chan band and writing down the Slater determinant corresponding to that. And what's very specific about phases with topological order is that their excitations are fractionalized. They are anyons, so they are neither bosons nor fermions. And what this means is that their statistics is in between, is not bosonic or fermionic, but when you exchange two anyons, your wave function is going to acquire a non-trivial phase, exponential I theta here. And in some cases that are even more complex, a phase is not enough to describe the exchange statistics, but you have to use a matrix. And that's the situation where, even though you've specified the position of all the anyons in your problem, there's still a degeneracy, and then doing an exchange in that among those anyons, doing an exchange operation is going to correspond to a rotation in that manifold that is characterized by a matrix Q. Okay, but we don't really need that. I'm going to talk about abelian phases only, but that's a big motivation. Being able to understand and realize phases that have abelian or non-abelian anyons is a big motivation to study topological order in general and fractional quantum Hall phases in particular. So I can maybe give you a few examples of topological order. And a very famous one is found in the toric code, and it's very convenient because it's an exactly solvable model, and we have very few models realizing topological order that are exactly solvable. So this one is very convenient for this, but it's a bit of a toy model, it doesn't apply directly to materials. If you want a more realistic Hamiltonian that corresponds to a solid material, for example, then you're going to need strong correlation, and for that you're going to need to do numerics. And well, the first example of topological order in an actual, realized system is the fractional quantum Hall effect that we've talked about a lot yesterday. So it arises when you have a strong magnetic field going through a two-dimensional electron gas, and it's characterized by a fractional quantum Hall conductivity. So it's a chiral form of topological order, and it has broken time reversal symmetry because, well, since the Hall conductivity is not zero. And most basic example of fractional quantum Hall effect is the 1/3 fraction, which has Hall conductivity equal to 1/3 times the square over h, the quantum of conductance. And the excitations for this phase are anyons, which have a charge E/3 and an exchange statistics equal to 2 pi over 3. And just to be very general, we can also cite another example, which is the example of quantum spin liquids. So not all quantum spin liquids have topological order, but some of them do. And we have examples that correspond to the same type, the same universality class as the toric code. And there are also examples with the same universality class as the fractional quantum Hall effect. So we have very diverse physical systems that may realize topological order. In all cases, if we want to study them, they have the Hamiltonian has strong correlation, so it's a hard problem that requires numerics, which is already a motivation. But focusing on the fractional quantum Hall effect more specifically, what are the motivations to do numerics with it? Well, there's a really long history of using numerics to study the fractional quantum Hall effect, and it's been very successful at helping us understand this phenomenon. And well, so first of all, in the continuum, to understand its topological order. So, for example, yesterday I talked quite a bit about the Laughlin wave function and about the fraction 1/3 of the fractional quantum Hall effect, and I said that the fractional quantum Hall effect at 1/3 is very well captured by this Laughlin wave function. And one of the reasons we know that is because we've been able to do some, for example, some overlap calculations and other things that have convinced us that the ground state at nu equals 1/3 is well described by the Laughlin wave function. And other proofs of topological order, such as the measurement of a fractional charge and fractional statistics experimentally came afterwards. Other things like knowing what is the value of the gap or the value of the correlation length in the fractional quantum Hall state, those are all things that we know thanks to numerics. And the second motivation for doing some numerics in the fractional quantum Hall context is to try and realize it in the absence of a magnetic field. So that's in principle feasible if you have a Chern band that provides you the intrinsic topology that you need and that removes the need for a magnetic field. Magnetic fields in general are quite impractical, and there are reasons to want to get rid of them. And one of them is to try and proximity couple the edges of a fractional quantum Hall system with a superconductor. And of course, the superconductor is not going to like it very much if you impose a very strong magnetic field. So this type of project is one of the motivations for to try and realize fractional quantum Hall state without a magnetic field. And again, to make contact with the things that I talked about in the past lectures, we don't know how to do this yet, but I think the arguments from numerical calculations have motivated experiments that have really shown a lot of progress in this field. And so so we have example of fractional Chern insulators, so fractional quantum Hall states requiring a lattice, but with still a non-zero magnetic field. And I talked about two of them. One of them was realized in Andrea Young's lab. And basically the fractional Chern insulator states arises around 25 to 30 Tesla. And much more recently, there was evidence in a different sample of a magic angle twisted bilayer graphene aligned with hexagonal boron nitride of a fractional Chern insulator at much lower fields. So this is a field where there's really tremendous and super impressive experimental progress. Well, I hope that things can go even further, and maybe numerics can motivate that a little bit as well. Okay, so what are signatures of topological order, and more specifically of fractional quantum Hall physics? So when we talk about numerical signatures, very often, as a general principle, it's good to try and find bulk signatures. The idea being that you want to minimize finite size effects. And that's because when you're doing a many-body calculation, very often you only have access to a small number of system sizes, and those sizes are going to be super limited due to the exponential growth of the Hilbert space with system size. And no matter what method you're using, finite size is probably going to be a limitation. So to minimize finite size effect, it's good to use a geometry with edges, without edges, sorry. That has that's a kind of a generic principle. This is especially true for topological phases, because if you don't have any edges, then you have a fully gapped system, and numerically that's good for numerical convergence. So in the context of exact generalization, that often means using the torus geometry. Actually, in fractional quantum Hall physics, we also use the sphere geometry, but so that's not very relevant in the context of lattice systems. If you have a lattice system, it's the most convenient is to have periodic boundary conditions. That's the torus geometry. The additional advantage of this geometry is that you have the maximum amount of spatial symmetries. So you can use the corresponding quantum number, the momentum on the lattice, for example, to block diagonalize the Hamiltonian. So that will reduce the size of the blocks when you diagonalize the Hamiltonian within a restricted Hilbert space, restricted to one quantum number. The other possibility is to work with the cylinder geometry. If you, in some cases, you can work with an infinite cylinder, which means just that you're using a translationally invariant ansatz. And that's going to be the case if you're doing, if you're using the density matrix renormalization group, DMRG. And in fact, an infinite cylinder has the same topology as a torus. So it's also a system that doesn't have any edge. So within all these systems, the main methods are going to be to look at the spectrum, most often the energy spectrum, but it could be an entanglement spectrum as well, as I'll discuss in the lecture. And you can also compute directly some observables. In the fractional quantum Hall context, the most obvious observable to look at is the Hall conductivity. So you can also compute the Hall response in this system. But in the interest of time and to keep this lecture self-contained, I'm going to focus on spectroscopic signatures of the fractional quantum Hall effect. And let me start with some signatures on the torus geometry. So signatures that are best suited to exact diagonalization. So generically, it can be shown that the degeneracy of the ground states on the torus is equal to the number of topological sectors. As an example, for the Laughlin 1/3 states, there are 3 topological sectors, which correspond to the vacuum, which has charge 0. So the vacuum is always included among the topological sectors. Then you can have one quasi-Hall, which has a charge E over 3. And then you can add another quasi-Hall, and that's going to have a charge 3 over 3. If you add an extra quasi-Hall, you form a whole charge E fermion, so you're basically back to the vacuum. So there are 3 topological sectors. So what's expected in the thermodynamic limit is to have a 3-fold degeneracy of the ground state. Additionally, you expect a gap to higher energy excitations because those phases are incompressible. And you don't have any edges, so there are no edge states within the gap. So here is an example that I think I already gave yesterday. So this is the quantum Hall effect in the continuum. The Hamiltonian that I'm using is the Coulomb interaction projected onto the lowest Landau level. And here I'm showing the low energy spectrum for 8 fermions and in 24 flux quanta on the torus geometry. And I'm using the center of mass momentum here as a quantum number to label all of my eigenstates. So which means I have used that quantum number to block diagonalize the Hamiltonian, and I'm doing one diagonalization for each value of the center of mass momentum. And as noted yesterday, and as is very clear here, this ground state is 3-fold degenerate. So this is the ground state here, highlighted in blue, and it has a gap to higher energy excitations. Yeah, so the good thing about this this method is that it's universal, right? So it should not depend on the Hamiltonian, and so you can use it to diagnose a new Hamiltonian. For example, if you don't know what is the nature of the ground state of this Hamiltonian. And that can be the case if you have a lattice model with a Chan band and some interaction, and maybe it is a finite bandwidth or something like, or non-homogeneous Berry curvature. So you cannot know for sure just by looking at the Hamiltonian whether the ground states will have topological order or not. So you can use the same method to do that. Was there a question?
Yeah, I think can the usual counting of excitations in the locking state be seen with ED?
Yes, if I understand the question correctly, this is what I'm going to talk about next in the next few slides. So I'm going to answer that very soon.
Thanks.
Yeah, so right now I'm talking only about the ground state when I'm exactly at filling 1/3. But then in the next slide, basically, I'm going to be adding quasi-holes in my system and looking at the degeneracy of the ground state there. And I think that's exactly, yes, that's exactly what you can do with ED. Yeah, so here I'm using the model from yesterday and from so the magic angle twisted bilayer graphene model with an added mass due to alignment with hexagonal boron nitride, which means that I have a conduction band that's separated from the valence band by a gap. So I have a churn band and I can project the Coulomb interaction onto the conduction band. And here, for the purposes of pedagogy, I'm assuming spin and valley polarization, even though we know that might not be the case in the realistic system. So I'm considering 10 fermions on 30 Murray unit cells. And so this is the low energy spectrum that I showed yesterday, but probably a little bit fast. So this is low energy spectrum. Again, I'm labeling all my eigenstates with a momentum. And here you see that I have a linearized momentum. So on the lattice, I have kx and ky quantum numbers. So I could represent the spectrum in this 2D space, but to avoid having a 2D a curve plot or something like this, I'm just linearizing it to have everything on one line. So those are my 3 almost degenerate eigenstates separated by a gap from higher energy excitation, which is a sign that I'm in the same phase as the low-field 1/3 state. And something that's very important with any numerical method, any finite size calculation is I cannot trust what I get from just one size. I need to do the calculation several times for several different system sizes. And compare the results. So here I consistently get this 3-fold quasi-degeneracy with a gap that's okay. That depends a little bit on size, but seems to remain finite as I go towards the thermodynamic limit here. So 1/ns is 1 over the number of Murray unit cells. And in red is the splitting of this degeneracy. So in finite size, there's no reason why the degeneracy should be exact. It's only exact at the thermodynamic limits. Because the sizes are a bit small, within hexagonalization, it's hard to see that it goes exponentially to 0. So we're just happy enough to see that it remains small and it remains much smaller than the many-body gap. So let's now move on to quasi-Hall excitations. So we know in the fractional Coulomb Hall effect that quasi-Hall are non-trivial anionic excitations, and that's going to have consequences for their degeneracy that we can diagnose through exact thermalization by looking at the energy spectrum when we have quasi-hole in the system. So to add one quasi-hole, we add one flux quantum. So again, I'm taking the case of a 1/3 Laughlin state. So I've shown again the 1/3 case. So like I'm back to the continuum now. So this is 8 electrons in 24 flux quanta. Now I'm adding one quasi-hole, so I'm adding one flux quantum. And this is now the energy spectrum that I am getting. As you see, it's a bit different. So its main features is that I still have a gap, but now the ground state, instead of being 3-fold degenerate, it has a degeneracy 25. And if I add two quasi-holes, I have a much more complex, much more complex spectrum, still with a gap, and actually 117 states below the gap. Right, so those are the main features, and we can actually understand those numbers, and we can predict them for at least for the Laughlin quasi-hole excitations. And we can predict them through Haldane's fractional exclusion principle. So this principle is it's a principle that states that the degeneracy of quasi-hole states is given by the number of configurations that satisfy a generalized Pauli principle. And when I say a KR Pauli principles, it means that I should have no more than K fermions in R consecutive orbitals. So I'm going to give an example right away to show what that means. Again, using the Laughlin 1/3 example. So for the Laughlin 1/3, K equals 1, R equals 3. And let's start with the ground states. So I'm starting to be as simple as possible. I'm using 2 fermions. And first of all, I'm going to consider 6 flux quanta. So I have a 1/3 filling fraction. So I should find the 3-fold degeneracy that we know there is for the Laughlin state. So the way to read those configurations is the following. So I have a number for each Landau level orbital, and the number just corresponds to the occupation of this Landau orbital. And 1-3 exclusion principle means that if I have a particle here, I cannot have another one here or here. And because I have also periodic boundary conditions, because I'm on the torus, I can also not have one here or one here. So the only option is to put the second fermion here. And I can also translate that whole configuration using the periodic boundary conditions. So I have in total 3 configurations that satisfy the 1-3, no more than 1 fermion in 3 consecutive orbitals principle. So I have 3 states, and energetically that would give me this, and that's of course a super simple spectrum because the Hilbert space is super small for this case. Let's now add 1 quasi-hole, and that's done by going from n phi equals to 6 to n phi equals to 7. So now I have 1 more orbital in my sequence here. So I have added a 0 at the end. If I take the first ground state here, I've just added a 0 at the end. I've added a quasi-hole at the end. And then the degeneracy of this quasi-hole is just going to be associated with where exactly I put this quasi-hole. So I'm going to get 7 of them, which is the number of orbitals in total. And that's going to become more complex as I add more quasi-holes. And energetically, that's again what I get. Those are the 7 states here, and then you have a few of the states there. So now, very importantly, I should emphasize that this is just a counting principle. So that's super powerful that we can predict this number of states. If you want to know where that comes from, that's related to counting the number of polynomials that have a given vanishing property. So in this particular case, you're counting the number of polynomials that vanish with power 3 as you bring 2 particles to the same position. Remember that the Laughlin state is Zi minus product of Zi minus Zi to the 3. So it satisfies this. And that's a little bit more complex when you're on the torus geometry, but basically the argument, the more rigorous arguments can be written down on the plane geometry using those polynomials. But those are not eigenstates. Okay, so those configurations, each of them, they are effectively, they're product states, right? If I'm just looking at one of those configurations, it's a product state. I've just put one particle in the first orbital and then another particle here. And the Laughlin, that's not the Laughlin state. The Laughlin state is a sum of many such configurations. And actually, they're not all included in there. So it's much more complex than this. But okay, it's a counting principle and it works. Right, so now going back to my more complex case, I can do the same thing, I can write a small script that tells me how many configurations are there with 8 particles in 26 orbitals. And if I only keep those configurations where there are no more than 1 particle in 3 consecutive boxes, and that's going to give me 117, which is exactly the number of states that I have here. So I can use that, as a way to diagnose a fractional quantum Hall state. Now it's nice. I can go even one step further, and instead of adding quasi-holes to my system by changing basically the Hilbert space, because I'm adding a flux quantum, I can also do it without changing the Hilbert space by from the ground states directly, the Laughlin ground states. Well, or what you think may be the Laughlin ground state, but you want to check by calculating an entanglement spectrum. So the idea of the entanglement spectrum is you start from the ground state psi, and you cut your system in 2 parts, 2 complementary parts, A and B, and you calculate the density matrix rho A associated with subsystem A by doing a partial trace on the density matrix psi psi. And this can be thought of as the exponential of minus the entanglement Hamiltonian. And this entanglement Hamiltonian, if you compute its spectrum, it's what we call the entanglement spectrum. So this is very generic. So how do we get quasi-Hall excitations from this? For that, you need to do a specific type of cut. So not all cuts would give you the degeneracy of quasi-Hall excitations, but a particle cut will do that. So what's a particle cut? It means that the 2 subsystems I'm thinking of when I say subsystem A, subsystem B, they're not like the physical, geometrical 2 parts of the system, but they are in terms of number of particles. So for example, if I have a system with 4 particles, that's n, I may do a partial trace on 2 of them Na equals 2, or NB equals 2. And so I get the reduced density matrix for a subsystem with 2 particles. More practically, we do Schmidt decomposition most often rather than building the reduced density matrix, but that's the same thing. It means decomposing the ground state psi into a sum over 2 complementary Hilbert space where the psi A and psi B wave functions are orthogonal. And I find it also helpful to write down the partial trace as an integral, because that helps me think of what kind of cut I'm doing. And in a particle cut, when you're doing the partial trace, the integral is over the whole system. From one, if I have a torus, it's over the entire torus. But I'm integrating over only a subset of the coordinates for the particles. If I did a geometric cut, here I would not have a product from 1 to NB, but from 1 to N, all of the particles. But then I would integrate only from 0 to L, for example, and then from L to 2L would be left free. So that's a way to extract the degeneracy of quasi-holes from the ground state, as was shown in this paper. So in practice, what that means, for example, taking again the example of the magic angle twisted bilayer graphing system that I had, I can start from the ground states, the threefold degenerate ground state, and I can compute its particle entanglement spectrum. So I had, in that ground state, I had originally 30 Moiré unit cells and 10 electrons. So I'm going to keep 30 Moiré unit cells, but I'm going to do a partial trace, so I only keep 4 electrons in that system. And this is the entanglement spectrum, which can still be characterized and labeled with lattice momenta for the reduced subsystem. But also, okay, so what's really important here is that I have a gap in this entanglement spectrum that's marked by the blue line here. And I have some number of states below the gap. That's also given by the Haldane fractional exclusion principle, the 1-3 exclusion principle. And the way to find it is to calculate how many configurations do I have of 4 electrons in 30 flux quanta. So 4 electrons in 30 orbitals that satisfy the 1-3 fractional exclusion principle. Or equivalently, I could also compute the energy spectrum of the fractional quantum Hall system with 4 electrons and 30 flux quanta, and I would get a gapped energy spectrum with the same number of states below the gap as here, so 9,975 states. So that's actually a really robust way of diagnosing topological order, because it doesn't happen by chance, right? Having a gap is what makes this robust, and then you have this number, plus or minus 1, and it's not the same number. So it's something that's that's a very robust way of diagnosing topological order. Right. So I'm done with this part of. These are basically the main ways that you diagnose the fractional quantum Hall ground states when you're doing exact normalization. You basically walk in the torus geometry and look at these degeneracies. There's another way which is most helpful in the cylinder geometry, and is most helpful when you're doing geometry, for example, and it's through the edge spectrum. Okay, so you know about the bulk edge correspondence. It tells you that if you have topology in the bulk, it's going to be accompanied by gapless edge states, and the nature of these edge states is in one-to-one relationship with the topological order in the bulk. And in fractional quantum Hall states, this is especially true. And we can actually describe the edge spectrum by a conformal field theory. The wave function in the bulk is actually given by conformal correlators of the same conformal field theory that describes the chiral critical edge. So taking the example of Laughlin states, and this is actually the same for all Laughlin 1/m, but especially for Laughlin 1/3. Then the edge is described by a U1 conformal field theory. And the result is that this edge spectrum is a chiral edge spectrum which has a very specific shape. So the velocity for this chiral edge spectrum is actually non-universal, but what is universal is the degeneracy of each state. So here what's important is to be able to have a momentum, to know the momentum of each state. So if you need to know, you need to label your eigenstates with so here an angular momentum, so that you can distinguish this sequence. And those degeneracies are tabulated in conformal field theory books, but in the case of the Laughlin 1/m states, this is what you get. So you can use that either from the energy spectrum, and for that you need to work with an open geometry, so maybe a disk geometry, or like or an hexagon or something like this, depending on the symmetries of your lattice. Or you can work on the cylinder as well, and energetically you can actually diagnose the topological order of the ground state this way. But similarly to what I explained for bulk quasi-Hall excitations, you can also work with a geometry without edges, and find out what is the edge spectrum through entanglement spectroscopy. So here, the idea is to do a physical cut. So earlier I talked about a particle cut, now it's a physical cut, where you're doing the integral over all the particles in the system, but with a reduced window. And I'm showing a cylinder here because it would be actually quite inconvenient to do it in the torus geometry, because when you do the cuts, you would end up with two edges, which would be a bit hard to read actually if you have two chiral states on top of one another. So it's actually super convenient to use an infinite cylinder geometry, which is something we can do in the context of DMRG. Then you'll end up with just one edge in your entanglement spectrum. It's actually something you get for free when you do DMRG. And it can be shown that there's a general relationship between the edge spectrum and this entanglement spectrum. And now can show you some numerics related to that, not in Moiré, but in a different model, in a different channel insulator model. I believe it was in the Haldane model. It's actually from our chat today, although this wasn't planned. But okay, so this is the entanglement spectrum corresponding to the ground states at feeling 1/3 for the Haldane model. And there are different colors corresponding to different charges. So one needs to focus on this light blue color. And you see that it has a chiral spectrum. It has a chiral shape with exactly the degeneracies that are expected from conformal field theory. So again, that's a super helpful way to diagnose a Laughlin topological order in using numerics, and here using GMRG. So finally, I want to end with a little summary of these different techniques. So I'm not claiming at all that I've given you an exhaustive list. There are other ways. In particular, I haven't talked about extracting the whole response. And that's a quite important way of doing that. So I've talked about hexagonalization on the torus, and I've told you there was, you could extract the ground state degeneracy. It's a first signature of topological order. The reason that you want to do more than just the ground state degeneracy is that when you have a symmetry broken state, it also has a ground state degeneracy. So you need to go one step further to distinguish between those two possibilities. I've also talked about finding the quasi-hole degeneracy to the particle entanglement spectrum, and that will actually help you distinguish whether you have a true topological order or just a symmetry breaking phase. Then on the cylinder geometry, especially using GMRG, you could find out the whole conductivity, especially through flux insertion. I haven't talked about that, but that's a quite practical method that's very often used. And as well, I ended the lecture by talking about how to extract the S spectrum from the entanglement spectrum. As I said, it's not an exhaustive list, but these are signatures that I find to be, that the community finds to be very robust and that are typically very convenient to extract. And I'm going to end here, and thank you all very much for your attention and your questions. I'm hoping there will be more today that I can answer. So I'm happy to take any questions. Hello, can't hear anything. Hello? Okay, I can hear you again.
Yeah, sorry about that. My internet somehow just.
Oh, okay. So it was you. It was not me. Okay.
I don't know. I hope it was me. Okay. So, but there's a question. Sorry about that. What tools do you use for both DMRG and ED? Okay. Very complex program. So. I have it depends. So for ED, I have my own codes. And for DMRG, I use StanPy. So it's a program that that's based on Python, that you can find and download, and that was developed by Frank Pullman, Mike Zalatel, Roger Mong, and now I think Jonas Hauschild has done a lot of good contributions, and I think many others in these fields. So I think now it has a pretty good documentation that can be found
online. So, and I think it's relatively easy to use. But I haven't used any other DMRG code, so I can't really compare.
Okay, thanks. Any other questions? So maybe I have a question, maybe on, I mean, maybe a philosophical, not philosophical, but like, so you said that, you know, our experimentalists are going further down in magnetic field to maybe find the fractional Chern insulator. Is there anything that you think they should be doing to do, or is there a way to avoid the problems that they see? Because I believe they see like other phases competing and so on. Is there any platform, or like is there any other twisted system, or are they all equally kind of constrained? I was going to say bad, but I'm not going to say bad. Constrained by these problems.
Yeah, it's a good question, and I was going to answer, maybe try in other Moiré systems. I think at this point it's really, you know, from my point of view, I wouldn't be able to really make a statement on which Moiré should be best for that, and as long as you use one that has a, you know, well-defined, well-separated Chern band from other bands, which is in principle the case in magic angle twisted bialeographene, aligned with hexagonal boron nitride. And there are other Moiré systems that in principle do that as well. So maybe there'll be, I don't know, more coming from what is it, twisted mono versus bilayer, like a single monolayer, bilayer twisted at magic angle, or something like that also has a Chern number. And the main, I think the main issue, at least that's the interpretation right now, is the current experiments that still require magnetic field, is that the Berry curvature in the zero magnetic field magic angle twisted bialeographene may still fluctuate too much. I don't know, given that this is the Berry curvature, and as well as the bandwidths are parameters that are super sensitive to microscopic conditions, it's really hard to be predictive about this. And I think what we have right now is you know, I would base my exploration more on what is already seen in experiments at integer filling. So if you already have a pretty strong quantum anomalous Hall effect with you know, hysteresis signaling orbital ferromagnetism that goes quite far in terms of filling fraction, and that includes one of those target fractional filling fractions we're interested in, that would be a good thing to start from. But that was the case in magic angle twisted bialeographene. But okay, there's I think there aren't so many samples of that actually do that, so maybe there will be more, and we know there's a variety from sample to sample, so it could be that in the same Moiré system this actually works, just in different sample.
There's another question by Mikkel. Can you get an actual energy spectrum from DMRG, for example, for each K sector along the cylinder?
Yes, you can. So in DMRG, the way I would do this is, first of all, I would work in a basis that preserves K along the periodic direction of the cylinder. So then you can find pretty easily the ground state in each of these K sectors. And then the second thing you can do, if you want more than one energy state per K sector, is you can you can project, basically, you can project out the ground state and run the MRGs multiple times. So the first time you get the ground state, the second time, with the added term with the projection of the ground state, you get the first excited state and so on. But that's a bit costly. So you could get it if that's really what you wanted, but it's also typically more convenient. If the goal is to diagnose topological order, it's more convenient to use the entanglement spectrum.
Very good. So I think there are no more questions, but you're in the Slack. So if there are more questions, I'm going to direct people there. And
sounds good.
Thank you and all the speakers of this session, and see you everyone tomorrow for a hands-on session. And yeah, so see you all tomorrow. Thank you.
Thanks.